It is my pleasure to begin introducing this. I'm Andrew Williams at Tufts, and I'm going to be talking about, in general, what the mission of the work group is, and putting it in context of OHDSI's broader ecosystem, laying out some of the very high-level aspects of the tool chain that's been developed by the GIS work group and how it fits in with that ecosystem. So that's going to go over not only the ecosystem, but the specific use case that's going to be driving the demonstration, the data and the code that are going to be used. For those who aren't familiar already, what geocoding involves, and then the specific way that it was done for this demonstration, and as a prototype for how this entire tool chain handles um, interactions with geocoding strategies. Other strategies for searching for and configuring geospatial data for integration with EHR data, the ways in which that geospatial data can be brought into contact with the OMOP clinical data through an OMOP extension for GIS, a really tremendous amount of work that's been done in representing especially social determinants of health and toxicants in standard vocabularies in the same way that the clinical vocabularies are. So a little bit about the work group. It has created this tool chain that I've just described. You're going to be seeing the details of here. And in essence, the overall goal is to make the geospatial data that's relevant to health useful and usable in the same way that clinical data are made useful and usable by the rest of the OHDSI. OMOP, its schema, the vocabularies for standard representation. So in the same way that those are, the data are normalized to this common data model, OMOP, and there's an extension for place-related data that supports multi-scale analytics, and that's what we're going to be showing you about today. So just a little bit of background for those who may be here for the first time and haven't been in touch with OHDSI for a long time. So it's we're a global community is dedicated to generating reliable evidence, specifically evidence that's needed by clinicians, by patients, by policymakers. I do that through a federated research model for the most part. So data holders keep their data locally. It's standardized, and so standardized analytics are brought to the data in order to conduct analyses, and results are synthesized centrally. It's large. Let me see, go back. It's large and it's impactful. It's used on a large scale to do things like inform decisions by regulatory bodies in the U.S. and around the world, as well as generate evidence that is, the main mission here. So the vision is stuff you can go into some depth on in the OHDSI's main page, but we take it seriously. It's all about innovation and reproducibility. All the work gets done through a community of contributors, mostly voluntary contributors. We do that work collaboratively. A lot of work really just wouldn't even remotely be possible with a large number of contributors who aren't, contractually obligated to be doing the work. We spontaneously find collaborations and pursue them. We do it in an open way that's consistent with open science practices, and all of it is for beneficent purposes. The federated approach that you probably saw, I won't go into this in too much depth. It's a slide that's often used. It's stolen from, I don't know, Patrick or George, but in essence, you've got, as we said, data that's been mapped to this OMOP common data model. It's held behind a firewall locally, and the standardized analytics are brought to those data. In the meantime, the community is working on things like developing standards, developing open source code that works with data in those schema and standards, applying methods, a very robust methods community that's testing and empirically evaluating which analytic methods perform best and implementing those in those tools against those data, bring the whole thing together in study packages that get sent to the people in this federated network where they run those packages locally and then send the results out for dissemination, central standardization. It is, as we said, large, and geographically, you can see a little bit about how large it is there. Those numbers that George shared earlier, Symposium are, I guess, still the best numbers. About 12% of the world's population has their data represented in this OMOP common data model. And the main things to be aware of here are that the clinical data, the data that you're actually capturing and transforming and putting into the CDM, have this relational structure. It's person-centered. Persons are related to visits. At those visits, conditions are noted, drug exposures and procedures are occurring during those visits. Measurements are taken, lab values, and so on. They all, using that relational structure, provide a longitudinal picture of what's happened to patients that's integrated in the main work that makes all the magic happen is in that central vocabulary part, in that sort of peach colored rectangle where it says concepts, vocabularies, and so forth. Those are used to take whatever the data looks like at an individual site. My lab values at Tufts are going to look different than Robert's in Stanford, where Robert works. No, Robert doesn't work at Stanford. But they would look different if he were. And the local values there are mapped to a common standard so that the code and the meaning and the interactions with the data are all standardized and can be leveraged for scalability and reproducibility and so forth. So not going to go into more depth on that here. I think the one thing I will note is that all this standardization so far in the OHDSI community has really covered the kinds of terms that are used in clinical settings. They have not covered the kinds of geospatial data that we want to represent in a standard way. And to do that, we've had to extend the vocabulary, and they're different in kind. Whereas there's a lot of agreement about what diseases are and what drugs are, there's less consensus about how complex ideas like social determinants of health actually live in the world and how to divide them up and how to organize them and so on. And so when Paulina specifically has extended the OMOP vocabulary to include this kind of data representation, it's a bit of a different beast. It's a different task. I mentioned that standardized analytics are brought to the data that are in the standard form, and there's a large set of standard libraries that are used for everything from querying data and managing it to visualizing it, but most importantly to analyzing it in various ways. Those are a part of a mature community of software developers and maintainers who have a public repo where it's over 240 packages live. Those have code coverage and dependency information and apply best practices for making sure that software are reliable and usable across the community. All of that is put together, the data, standardized analytics, and so forth in a standard way for research. You first look at the data that are in each of the distributed data members' data sets, see if they are suitable for the question that's going to be asked. And if not, if diagnostics are failed, those are not meant to go forward. Similarly, the phenotypes that you develop from those standard concepts can be examined and see if they are sufficient. They're capturing the exposures and outcomes and populations that are needed for the study. And if not, you stop there. And then, depending on the kind of analysis you do, there's going to be various presuppositions about the analysis that have to be met in order for the results to be valid. And similarly, you would stop if those are not met. And if they all are, they're all contributing to the federated results at the end of the day. So that goes from the upper left-hand corner to the bottom right-hand corner. That's the overall approach. There's a variety of tools that support those diagnostic evaluations. This one is illustrating what we often use at Tufts and federated networks that we're helping to, that we're working in to evaluate the comprehensiveness of data and its quality and so forth. There's tools called ARIES and Data Quality Dashboard that do that. There's other tools for evaluating the phenotypes that have been put together and looking at that with appropriate expertise weighing in. And then there's a variety of tools that are looking at some of the analytic assumptions and whether they are met. Beyond that, there's a variety of support that the community provides that helps educate people about how all of this works. There's the Book of Odyssey, hundreds of hours of YouTube videos and tutorials, of which this will become one eventually, probably. Open courseware that's been completed by hundreds of people around the world. Other engagement strategies, including a regular community call, vibrant public discussion forums that are grouped by where you are in the community and the kind of things you're interested in, and geographic chapters, North America, Europe, APAC in the Asia Pacific region, Africa, and India is a newer one. There are asset libraries, so when people have, so all that standardization enables reuse, so people have spent a lot of time validating and building a phenotype that lives in a library with metadata about who did what and what it's for. Those can be reused. There's prediction model libraries with metadata about how those go, and all the code is according to standard open science practices is preserved publicly and is available for reuse, and this has resulted in hundreds of publications and a really innovative approach that shares all of the results at data.odyssey.org and provides tools for browsing and working with those data. So that's the larger ecosystem that it all exists in. And it's been with a goal of extending that ecosystem to include geospatial data that we said we've been working on, and that includes the vocabulary extensions, which covers GIS-specific vocabularies, shapes, and so forth, a toxicant vocabulary, and an SDOH vocabulary. And Paulina is going to be going into that in a good deal of depth. The extension of the OMOP schema is not called the environmental exposure table. We've been trying to standardize our nomenclature over the last few days. It is now the external exposure table. And there's a strategy for cataloging and for working with GIS, as we said. All of this depends on a slight tweak to the most commonly used version of OMOP. It harkens back to a slightly earlier one that includes the location history table. We'll talk about that, but that's the main pieces of the extension that are required to work with these data. So this picture shows typically how reliable evidence is generated. On the top part, the green on the upper left of this shows in general what you're doing in a typical Odyssey study. You're taking health information about health states, about clinical care, and about care providers from some kind of healthcare setting. You're extracting it from wherever it's collected, transforming it, and loading it into this CDM and applying those best practiced analytics to generate the gold reliable evidence about health impacts that we're all seeking to use this routinely collected data for. The bottom part, where you see patient address information, geocoding, and so forth, begins with getting either geocoding your patient information, because you need to be able to connect where patients have lived to the geospatial factors that have influenced their health. But similarly to collecting those health state, clinical care, and provider information, you're collecting data on things like climate, on toxicants, on social determinants, finding those in the places where they live in public data sets, retrieving them, and then linking them through geocoded address information and adding them to this GIS extension and using that same whole ecosystem to derive standardized best practice derived evidence about health impacts that includes not only what they've been exposed to in a clinical setting, but all of those other geospatial relevant features. That's the basic workflow. So that all happens via a discrete set of things that can work with one another, some of which are optional, some of which are kind of a core part of an Odyssey specific part. They do require some version of geocoding of patient residence information. So yeah, there are tools that support this whole integration with different cataloging resources once those patient data have been geocoded. And a method for implementing standard transformations of the place-based data into staging tables before getting it into the extension for OMOP. And yeah, that handles all the spatiotemporal joins that are required, the vocabulary for representing those. And that's Again, all stuff you're going to see in more depth. Here's a little bit of what the schema are. Robert's going to go into more depth into all of this, but the schema that are used for transforming the geospatial data to get information about the source data itself, index it, and begin to standardize the data are represented there. I'm not going to go into any depth here. Robert's going to go into them in more depth in his section. And the right-hand side of that last one is the left-hand side of this. And in that aqua-colored box, you'll see the things that are part of the proper OMOP and OHDSI extension. And so those joins, those temporal and spatial joins happen from that left-hand set of things after they've been indexed and so forth, and are linked here to the rest of the data so that it can be used by the standard tooling. Just a little bit of a teaser about the vocabulary. So the GIS vocabulary, as I said, it mentions these, it covers standard concepts for geographies, boundaries, spatial elements. The toxicant vocabulary covers environmental substances, and the SDOH vocabulary covers environmental and societal factors that can affect health outcomes. There's a lot there, many really exciting things that are going to enable us to do all this work in a standard way. Here's some links that you can follow that will give you a lot more information. A lot of work has gone into documenting all of what you're going to see. And in the GIS work group, we are actively driving all of this work forward through use cases. And so if you have a use case and you think this kind of thing could be helpful to you, we are excited to welcome you. We don't need to drive your work for you. We can show you how it might or might not support your use case. If you want to contribute to some aspect of developing things, you can. We have a project management approach that enables people to take whatever their use case is and either just leverage things as they are or contribute to the development of it and provide support for what it is you're doing. We meet regularly, and you can find out all about that here. I'm going to introduce the use case. So to do all of this, we're going to, as I say, kind of demo this with an example. And so pulmonary health outcomes in particular, COPD, is going to be, we're going to use the ecosystem for defining a population and an outcome and an exposure that includes both geospatial data and clinical information. So it says here where it says pulmonary disease, Jared's going to go into a little more depth, others are as well, on what it is we're talking about here. But COPD, in essence, earlier exposure to particulate matter in the atmosphere, PM 2.5 levels around the world. How do they relate to the prediction of COPD is the task that uses this ecosystem. The particular piece of how that's done in OHDSI is the PLP package, patient level prediction. So yeah, OHDSI has packages and approaches for doing descriptions of data, how care is delivered, for comparing different kinds of treatments to see which ones have which effects and which work better than others, et cetera, and a very rich approach to predicting outcomes using a variety of modeling approaches. The basic framework, as for all OHDSI studies, you're defining either 2 or 3 cohort definitions using the standardized data. You're using either target and outcome or target, outcome, and comparator cohorts to do this. For prediction tasks, you have an observation window, a time at which patients are at risk for the outcome you're interested in, and you use features derived in the observation window to predict that outcome, and the standardized analytics all assume that you've defined a specific cohort in those ways that are needed for that. And it's very fully featured, this set of slides that you'll get afterwards, and the links to the PLP GitHub site and its documentation will tell you all about it, but pretty much any kind of model you want to implement in any feature engineering approach can take this standardized set of inputs, provide diagnostics and outputs, and allow you to browse them and do that very flexibly. We are doing that in a custom way, allow you to browse them and do that very flexibly. We are doing that in a custom way that Jared is going to describe. And now I'm ready to hand off to Tim.
Thank you, Andrew. Hi, everybody. My name's Tim Norris. I'm from the University of Miami. What I wanted to do right now is give you guys, GIS 101, just so we're kind of all on the same page as we start talking about some of these concepts around location. The key take home on this slide is that we layer data in GIS. And the other key take home on this slide is that there's two data structures that we commonly use in GIS. One is a vector data structure for discrete features on the Earth's surface, points, lines, or polygons. For example, census tracts, cities, or roads. And then the other data model we use is the raster data model, where we model continuous things on the land surface like elevation or land use. And I will say right now in this working group, we've worked very extensively with the discrete data model, the vector data model, but we have not delved into the raster model so much yet, but it is in our future. So we'll be talking mostly about those discrete features today. These are very common tools that you can get for your desktop to work with GIS data. The Esri suite is kind of one of the industry standards here in the US, and QGIS is an open source piece of software that grew mostly out of Europe. It's a fantastic tool, and it really depends. I think I use them both. I don't have a preference really either way for one or the other. But if you use the Esri tools, both of them have large teams behind them, I think is the key take home on this. Whoops, slow down. These are common database backends. I know a lot of people within this community use PostGRE SQL or use some other thing like Microsoft SQL Server or something like that to serve their databases. Right now, we're working with PostGRE SQL and PostGIS. It's a geospatial extension for PostGRE SQL. But I know that all the big database management systems have geospatial extensions at this point. So just for the purpose of this talk, we're going to be using these two, but it doesn't limit us to this at all in any way. And then these are common tools for analysis, and I think it plugs in really well into the tool chain here in the OHDSI community, where you can easily plug that spatial extension into an R analytics suite, much like Hades or something like that. And these are some of the common packages that we need to add into that suite so that we can have access to the geospatial data. I'm a Python geek myself, but I know this community is more focused on R. And then there's two more things that I want to talk about really quickly before we go. Geospatial data, as everyone knows, works with coordinates, right? We have lat and long. In geospatial systems, there's two kinds of coordinate systems that are really important. This is like a bit of a joke. We always talk about this when we talk in front of our students that, how do you peel an orange? And it makes the idea that you have to make things flat. You have to break that surface somehow. You can't take lat long and make it a flat surface without breaking something. And so we use this joke that, how do you peel the globe? This is a fantastic website, actually, how to creatively peel the globe. But anyways, um, we have these three things that we really need to pay attention to. I don't expect anyone to be kind of experts in this by the end of the day, but we do need to pay attention to this. There's two different ways of representing data. One is through lat long, which is this idea of a spherical coordinate system. One is through a Cartesian coordinate system, which is called a projected coordinate system. If we want to do any measuring, which I think is important within this community, measuring distance, measuring things like that, we need to have our data in that projected coordinate system to do that measurement. And these are just some numbers to remember. You'll see 4326, 4269, very common. These are things you want to just be looking out for as you look through your data. I assume we're recording this, so I'll be here. This is really common stuff. I just want to bring your attention to it as we move forward. And then these are some words that you should be paying attention to. WGS 84 is a very standard center of the Earth. I don't know if you guys know, but there is no one center of the Earth. We don't actually know where it is. We just kind of set one and use that as our reference point. So WGS 84 is one of the standard centers that we use, so pay attention to that. And then here in the US, NAD 83 is very important if you're working in the United States. But for the rest of the world, it's mostly WGS 84. And then this is the last slide I think I have. Andrew mentioned this, that one of the things we really want to do is be able to join our data using spatial joins instead of column-based joins. I think the traditional kind of OHDSI model using the common data model is that you have the ability to do these joins based on key columns, but using GIS, we do it based on location instead. The key take home here is that there's several, these are the common ones that we think are going to be applicable in a lot of case studies where you have on the left-hand side, patients as points within some kind of polygon, and you can say, give me the patient info in this polygon, or attach the polygon info to that patient. And we heard about this yesterday, where you might attach the census tract ID to that patient or something like that. And then the other ones are these kind of buffers around things. Give me the distance around this pollution emitter, give me the distance around this healthcare provider or something like that, and then show me things inside that distance. So these are just common things that we use. And I think this sets us up. As I said earlier, we're not working with raster so much, but this is something you could do very similarly with the raster data model, where you say, give me the value at that location of the raster. And then this is that idea of a spatial join where you create a new column in your patient table that has some data from that feature, that polygon there. I think that's it.
All right. Thank you both for the awesome introduction. I will share my screen here and hopefully you all can see this. Then I'm going to dive into it here. So kind of going off of both what Andrew and Tim said, one of the things, or one of the first things that we had to do when putting together this broad demo was to create a data set with both the EHR and the GIS related data. Okay, so everything in the synthetic data set starts from what we have termed the Tufts synthetic data. So this is a data set that was built against the legacy Tufts system, which itself was kind of an agglomeration of a bunch of different health centers and data coming from that, all compiled into OMUP. So this company called Syntegra, which is now no longer, worked together with the team at Tufts a few years ago to produce via transformer models this set of representative EHR data, specifically in OMUP. And so this data set we've been starting to use and distribute more and more, and we're learning more about it, and it's supporting now a variety of different use cases. Now after this workshop, it supports GIS. But in total, it has about 500,000 patients, of which something like 50% have rich OMUP data, meaning they've kind of been involved with the health system more than once. Of course, in our standard EHR system at Tufts, we have many patients that come maybe one time and they just kind of exist as almost this orphan patient with not a lot of data. That phenomena is also captured in the synthetic data. So just to note, realistically, it's about 200 to 250,000 of rich data patients. The data was both trained on and developed against and output in OMUP version 5.3. For this demo, I converted it to 5.4. So we have now a 5.4 version, at least a subset of the data that's in 5.4, if you're interested in that. And in little side notes, the part of the educational activities within the N3C, which used to be the National COVID Cohort Collaborative, now has dropped COVID from the title. They are using it as a kind of for training purposes as a data set. So if you've been involved there, maybe you've seen it, or you might see it in the future in that context. Okay, so here's the next few slides, kind of just proving or some, I guess maybe even stepping back. Once the Syntegra company produced the synthetic data sets, the data was evaluated against, or data were evaluated against the real data set by an independent party, looking at various elements of the data sets. In this case, you're seeing comparisons of like fractions of or percentages of patients who have at least a condition or who have depression and kind of relevant disease profiles of interest. I have a little note at the bottom that approximately 1,100 individuals in the synthetic data sets have COPD or some more specific diagnosis than just COPD that's related to it. Just for reference there. So again, this is showing that the synthetic data is representative in some way of the real data sets. Again, you're looking at the gender, death, and age distributions, also consistent across the real and synthetic data sets. You'll note that, of course, the synthetic data set is a smaller version of the data set. So I believe they scaled up the deaths potentially. I don't know, Andrew, we can maybe answer any questions about that later. But if you look at gender and age, both of those track very well, and those are very relevant to what I will talk about later, because when we're creating the basis for the COPD model, we chose our non-COPD patients based on a gender and age match. So the fact that the distributions, at least in the synthetic set, represent our let's say real health system data, we have some bearing on both of those distributions to start with in that comparison. And then last thing I'll say about the synthetic data, so this company also did a correlation between comorbidities, or effectively looking at let's say patients who smoked and how often they had a stroke, things like this. So these plots are effectively showing correlations between disease types or disease phenotypes, or however you want to refer to them, in kind of this chart here. And so you can see that they align very well. So the left side in this case is the real data set and its correlations, and the right is the synthetic data set. Okay, so kind of switching gears now, as a demo GIS data set, so now we're not working with EHR data anymore, we're working with this kind of spatially oriented data where we have values assigned to a spatial location. We settled on a global data set that is available through, I believe, CDAC, as you see in the upper right. And these data were captured via satellite imagery. And so these are images that then they're able to extract based on the aerosol optical depth, kind of estimates of particulate matter concentrations. In this case, it's particulate matter PM 2.5, so 2.5, I believe, microns in diameter or smaller. And this is then distributed across the globe. And so what you see in this slide is effectively from 1998. How this distribution looked then. The data set actually spans 1998 up until 2016, as you see in the citation. So we have like every year an average concentration, and it's, again, importantly here, it's split based on what they're terming urban areas. It's kind of a loose term, but more or less like cities, but not, yeah. Like imagine different polygons around cities, if you will. And so that's how the data is distributed, and I'll get to more of that in just a second. But before I I don't know how dark it is in this room, so this might not show up well. This is a very cool plot that was created by Tim. So thank you, Tim, for this. That kind of gives a more detailed view that is derived directly from the data set itself. So I believe you visualize this. Tim, I don't know which of the desktop tools you used to create this. I don't know if you want to shout it out, but
QGIS says Tim.
QGIS, awesome. All right, great. So this is a QGIS based plot, and what I can do then is, as part of the creation of the synthetic data, I selected. We didn't use all of the cities, of course. There's like tens of thousands of cities being shown on this plot. I used a subset of only 20, but they are distributed, and I'll show. Sorry, they're distributed in this way. So all of these green dots are the cities that I chose for the data set, and slightly biased toward the northern hemisphere, but they have a nice distribution in terms of their PM 2.5 concentration, and that'll be more relevant as you see in a second. What does the data set actually look like? So this is a CSV modified version of the data sets. Thank you also again to Tim. So we have a city with an associated urban ID, and that city has, of course, it's the country that it's in and the continent that it's in and other information about it, how big the polygon is around the city. But then we have per year, we have the annual average concentration of PM2.5 in micrograms per meter cubed. And then what Tim has done is he geocoded this, which you'll hear more about in a later session, to assign a single latitude and longitude point to the city. And that's very important because it's relevant for the spatial joining that Tim also already mentioned, but it'll come back later when we talk about creating this external exposure table and assigning particular exposure values to people based on where they're located. Okay, but that's at a high level, you can imagine a big spreadsheet with these annual average values and a city together with a latitude and longitude value. And again, more to come in the catalog and geocoding sessions about that. And so Andrew already kind of mentioned this. I'm going to just briefly go through. Analytic use case was to combine the tough synthetic data with its representative EHR data in OMOP with the GIS data from this PM2.5 data set. We also wanted to create a subsample of patients. We didn't want to use our entire synthetic data set. We wanted to focus on the COPD patients and then the patients without COPD who represented those COPD patients in terms of their age and gender distribution. And with that kind of subset of synthetic data, we wanted to create a prediction model or patient level prediction model to understand and predict or try to predict the risk of COPD for a given individual if we know the pollutant levels that they're exposed to in their city of residence together with their EHR data, in this case in OMOP. So in terms of the data processing, again, I've already mentioned most of this, converted from OMOP 5.3 to 5.4. We selected a COPD cohort using a pretty simple definition, looking at just this COPD concept together with its concept descendants that Andrew mentioned briefly in the intro. In that COPD cohort, we identified about 1,100 individuals. We did this both with direct SQL query and with Atlas, and I'll talk about that in a few slides. And then we characterized the resulting cohort with regard to its age and gender distributions. And then what we did is we wrote some SQL code to actually select a subset of the non-COPD patients that aligned with those age and gender distributions. And I have a link on here. Take a look. There's an issue that's talking about synthetic data. I did a write-up of this data set and the code that I used to produce it there. So if you want more details about that, check out that link or just go to the OHDSI GIS page and search under issues for the synthetic data. All right, a little bit more details on those COPD cohorts. So this is a very, very simple cohort just for a demo use case. The cohort entry event was effectively a diagnosis or a first mention of a problemless entry of COPD or any of its descendants. We didn't have any requirements on continuous observation before or after, and we didn't have, or we only limited the events to the first per person. In terms of inclusion criteria, we didn't specify any. So once the person entered the cohorts, there was nothing that would otherwise exclude them. So we didn't look at other comorbidities, were they a smoker or not. It wasn't super detailed. We just said, okay, you're in the cohort, you're staying in until effectively your observation period ends, which is the exit event that we specified here. So again, keeping it very simple for the purposes of this demonstration. And this is where things got a little bit more complex, and I'm looking at time. I'm about halfway through, I think, my session, so I'll try to make sure I have, or more than halfway, I should say, and I have about a few slides left, so I'll try to get to this. But how did we actually assign those locations? So I mentioned before, we picked 20 locations from this GIS data set to place patients, these synthetic patients, in artificially. And so what I did is found a couple articles, or we found a couple articles, one of which gave kind of an expected global prevalence for COPD as of 2023, and the other, so that's the top left, and the bottom right gave expected odds ratios of COPD relative to PM2.5 concentrations. And so in this case, it's more or less trying to define a relationship between what the prevalence is, I guess, of COPD in a location with higher PM2.5 versus lower. And so in a crude way, I took the relationships from those articles, and I derived kind of this rough relationship between an odds ratio and the PM2.5 concentration, which then effectively serves as the forcing function, or like the underlying function that we use to distribute COPD versus non-COPD patients across our 20 locations. So again, this is loosely based on those papers, but some of this is just for the demonstration purposes. But just so you see it here, this is kind of the underlying function that I used. And again, odds ratio on the y-axis and the actual concentration, annual mean in this case, concentration PM2.5 is on the x-axis. And with that relationship, I was able to distribute my patients with equal amounts. So you see 334, I believe, per location into either COPD, those COPD patients or the not COPD patients into the different cities that I chose, which are here on the left. And I apologize, this is probably small, but yeah, I'm not going to say all the cities, but we can come back to that later. Yeah, so then that's effectively that distribution on this prior slide was what I used to determine the ratio of cases to non-cases in those locations based on their annual median, in this case, of 2.5 across that 18-year period. And so you'll see in these cities in India, there's a very high ratio of COPD to non-COPD. And if we get down to somewhere like Fiji or in New Zealand, where there was much less pollution as of this data set, we have very, very few patients with COPD. And so then what we did, and I have only 2 slides that are also talked about elsewhere quite a bit. So, and then the next slide, Robert will give some more details about this. But at a high level, we took those 20 locations and we distributed our patients across those 20 locations into this location history table. So our location table just has 20 rows with the cities and their lat long values, thanks to Tim. And location history then has actually 1 row per year per person in our data set, with the assignments of the people based on this kind of case to not case ratio. And we end up then with this long location history table that says these people are in city 1 based on the ratio that we expect, and so forth all the way down, with each person receiving a location history. Oh, getting ahead of myself here, apologies. So the location history actually has 1 entry per patient from either the start date of the GIS dataset to the end date of the GIS dataset, or from when that person was born to the end of the GIS dataset, whichever is longer. Whichever is makes sense in that context. So location history, they have 1 row per person, and we assume that the patients do not move out of their city for the entire period, and that's a key point. We're not assuming that people are moving around between cities, and that would complicate, of course, our the interpretation of things later on. So we kept it very simple again, 1 location history. More to come on that next session. And then once we had those tables set up, we used this kind of broader OHDSI GIS tool chain to take our location history table to perform a spatial join, where we take the polygons that I showed you and try to place these cities inside of the polygons in order to retrieve the value that the person was exposed to at that location at a given time. So the value of the PM2.5 for that person at a given time. And here in this external exposure table, we did actually have 1 row per person corresponding to each year that they were exposed, because we have a different annual value for their city depending on the year. So we end up also expanding in its external exposure. And this is actually the table that ends up getting referenced in the analytics pipelines. It has dates of exposure that are relevant. It has the person who is relevant. It has the value of the exposure itself. And it has our OHDSI GIS vocabulary terms, which will come up in a later session as well, that are nicely integrated into this whole process. So we're now, instead of referencing standard concepts in the OMOP vocabularies, we have this exposure concept ID, which is specific to the annual mean concentration of PM2.5 pollutant, which if you look in Athena, you will not find, but you can find it in the newly minted GIS ID space. Okay. that is more or less the making of the synthetic data and kind of how it's comprised. My last slide here is just a small note about if you would like access to this, there are ways to get access to it. The full tough synthetic data is accessible after you sign a DUA or data use agreement. And I believe that the synthetic version of that, or if you want to have this augmented GIS synthetic data set to play around with, will probably undergo a similar process for that. So it is available, but get in contact with either me or Andrew about how if you would like to start playing around with it. All right, and that is all I have for synthetic data.
Gaia is the title of this, but I'm going to try to cover how this ties together with the use case we have, as well as the parallel efforts that you're going to hear about later. But Gaia in general is the central core of what we're doing. That is basically the central dependency to which a lot of things are based on. Just to reiterate the problem space, relating place-related data to person-level data, specifically in OMOP. Did a great job explaining what kinds of data we're talking about. The example on the left is a polygon with a percentile of a poverty rating as an example of SDOH for something different, how that can be translated into a person. And in that blue bubble in general, what we're ending up with is person X lived in a certain location, geometry that had the same attribute. And for the sake of OMOP in the use case, that is what the end target would be. Guy in a nutshell, thank you, as an actual nutshell. Just to give the highest level definition, it's essentially a machine function that takes configurations of data sources and goes out, retrieves those data sources, ingests them into staging, translates them into our common model, which I'll show in a second, and makes them available for research. It's intended to be deployed in your local infrastructure behind your firewall, but separate from your CDM, and with connections between the two. It provides a community-driven, extensible approach for harmonizing, leveraging place-related data. Those of us who have incorporated place-related data before, it is a little bit of a Sisyphus situation where you don't get more efficient over time. Every time it is quite annoying. Gaia itself, in terms of the namespace, is intentionally limited in scope, where it's, again, serving as the foundational dependency, where if we can keep that static, it's a lot easier to build extensible functionality on top of it, as mentioned there. And a parallel here is the common data model and Web API and Atlas and all the tooling that you could build on that when you have a static foundation underneath it. Another view of that, not all that's going to make sense at the moment, but in general, what I mentioned as sort of the machine is we have these metadata configurations, which I'll show later on. Those get loaded into your database and then become variables to automate that process that I was talking about. That metadata would, the plan is to, and as Tim will talk about later, have that in a catalog that we can continue to build as a community, so that once one person solves DM 2.5, you just need to say load variable, whatever that ID is, and that's already taken care of. So it's a bit of a paradigm shift of doing things manually every time to now we're facilitating growth in a community effort, both on this side and the vocabulary side is also a notable side. Again, more of a namespace thing of what Gaia is. It's just solely referring to two specific pieces of it. I didn't mention before, but Gaia, Greek mythology, personification of the earth. Atlas was taken, so this is the best we could do with that. There are other components to it, but Gaia Core is essentially a service layer functionality. Right now, it's mostly in R. It's dealing with getting stuff into and out of what we call Gaia DB, which is a PostGIS database, as Tim explained. PostGIS is free. We again deploy it locally and separate. It's compatible with these R packages because it has specific data types built into it. Specifically, one is the geometry, which you'll hear about. And that really enables extensibility and interoperability with really most things geospatial. includes a geocoder inside of it, one of the two that we will mention. So that is one option to do that, and that is, again, completely local, especially with patient protected data. We're not sending stuff away from the servers, so that's, you bring down the database and geocode locally. And the backbone schema, the heart and soul of what enables what we're doing, is stored within this PostGIS instance. Here is an image of said schema, and I hope this all makes sense immediately, but it is a labor of love. We've done 2 steps forward, 1 step back for a while, but we've not cut corners, and it is at the point of maturity, as you'll see through these other presentations, where we're really taking off in terms of functionality, and there are avenues we don't even have the bandwidth yet to expand with based on what this provided. So there's a lot of opportunity to quickly expand, and is a good time to get involved in what we're doing because of that. In general, the data standardization portion, and just to do another parallel to OHDSI, I won't call it a common data model, but just a common data approach to this is, if we don't have to deal with all these disparate data formats, we can build functionality on top of that that expects the same format, and you can continue to grow from there. I'll show the metadata in a second, but the first step is literally going and getting the data, the URL, however it's released, whatever distribution service, if it's an API, doesn't matter. Go get the data, bring it into your environment, ingest it into staging. So that's Postgres, and that's where that Gaia core functionality would come into play. And here is the basis of it. It's essentially geometries and attributes of geometries. The simplest way you could possibly do that. There's scaffolding on top of that to make it all make sense and interrelated, but that's the approach we had. And a geometry is a data type in PostGIS that has libraries of functionality. All this geospatial functionality that you could need is there because we have them stored this way. One thing to note here is there isn't actually a singular geometry table or attribute table. We use templates. So each data source is split into its own geometry and its own attribute. And that's the result of, there's a reason people haven't made a geospatial common data model, because it would become massive immediately. So this is our solution, is that data-wise, efficiency-wise, they're all separate, but functionally everything's parameterized, and it's treated functionally as 2 very large tables when in fact they are separate. So that might be a confusing point. Here's the different view of that. The top level functional metadata section is what we're referring to when we say these configurations, or what would exist in the catalog. I'll show that in a moment. The indexing structures are just the mechanism to deal with this templating structure that I just referred to. Those are automatically generated from the data sources. And then on that lower section, the standardized data is the ingested data into these formats. It is worth noting, I'll go back on this one, that we have various types of what we call place-related data sources. Some that have shapefiles, geometry objects built into them, some that have lat long, but a lot of the time of those that are valuable, especially in this realm, it's just a geospatial identifier, a FIPS code, a GeoID, a reference system to a polygon existing in a different data set. So this example I have here on the left is a geometry that came from Tiger data, but on the right is the social vulnerability index. And so by using the shared identifier system, where even though the data sources that don't actually have geometries in them, we have them as dependencies to other data sets that do. So the metadata also serves as the inventory system, I suppose, of these IDs. These UIDs persist throughout the rest of this, so it's you're able to track everything we're doing there and use that functionally and in a parameterized way. I won't go through all the columns, but in general, we have descriptive metadata. We have that is related. The other side, which is related to going and getting the data and ingesting it. So what kind of data is it? Did it come in a zip file? Is it a CSV shapefile? What kind of boundary types it is? All the steps you need to get that into the system by just doing a load function, essentially. We refer to that as part of the functional metadata. And I'll show an example in a second, but notably within the realm of the functional metadata is on the bottom in the red, what we've I guess executable functional metadata, which is little tiny ETLs, is a good way to think of it. Of you have it loaded in your memory and you want to convert this into a geom or an adder attribute. And right now that is a R query, which makes this incredibly flexible, especially with the diversity of data sources out there where values can be in columns. The actual variable you're after is you pick from one column where this is that and this is that. So when we're saying we're taking variables out of data sources, we're deriving them in whichever way they exist. So that flexibility, geometry, it's straightforward, more straightforward than for attributes. You can see there's just a slight clause there where the convention either used name or name slad, depending, and just to cover that, but that's how you would then ingest that as a geometry object to then be used. And that gold little star you can barely see there is for these variable sources and the concept IDs that Plain is going to be talking about. One point to make here is that a variable source to data source is many to one. So a data source has many affiliated variable sources to that. So we have one data set, the PM 2.5 data set, or environmental data set with a lot of different factors to that. Each of those is going to have its own variable source record. We're able to add concepts to those, but then also maintain the provenance and the functionality to go get that. There's a lot of dependencies here, but for the sake of how flexible this is, we could say variable PM 2.5 load, and it will go through the entire process of getting all the dependencies, and that's the only variable that shows up in your data set. You don't need to get everything. This level of sort of separation can be quite helpful. And this is, I believe, the use case that is, or the configuration for the use case that Jared referred to, what that would look like. I understand it's hard to read, but in just general, it gives you the picture where the org and org set ID, those kind of descriptive pieces are how these templated pieces get their naming conventions and things like that. That's a polygon, has attributes, is essentially whether, again, a functional switch, if you will, for while we're loading that. A zip file tells it and use the first unzip it and do that. It's a shape file, use this R function to then load that. The actual file name after you've unzipped and done all that, the URL, so on and so forth. And the variables are the same way. And the other specs, I wouldn't go much further than that, but this flexibility is what we're talking about. We're talking about the catalog. This data source is a single row in a growing list of established use cases where we can automate everything to the point of having a standardized representation. And then getting towards the OHDSI side. So at this point, we have our standardized place related data. We have the tools to go to and from. Let's put it into OMOP. There are few difficulties with doing that we have tackled. As Andrew mentioned, it was version 6.0 that we must not refer to. This is all part of it, but we recently got it reapproved and stuff. So the things we're mentioning are about to be a part of what we're going forward with. But in general, OMOP's place-related data, or a person-centric data set, and we're talking about place-related data, and that conversion is non-trivial, and you need a lot of context and provenance. There's many different ways you can make that translation. As Tim was showing, taking a centroid, the closest. It's if you want to tessellate it. There's a lot of different ways where, if you're bringing an attribute of an area to a person, you need to persist how you did that, because again, it is an endless thing. And then, yeah, I'll just go through these one by one. Geocoding, as was mentioned before, OMOP has a location table. I believe the location table still has lat long, but they got rid of the projection as part of the 6 part. So it doesn't have what we need entirely, as Tim expressed, and it's sort of been the wrong spot for us. Geocoding in general is taking a street address and turning that into a place on the globe. In our circumstances, is turn that into a geom. So when we're doing that, it is in a privacy preserving way. We're talking about HIPAA type stuff. Addresses are most certainly on that list. So you'll hear about geocoding typically with Google services and things like that. We consider those just out of the question for this. Could have been used for the synthetic data probably, but two examples of what we can do locally are Gauss and Tiger geocoder, which essentially bring the entirety of all that data local for you to geocode that data and then delete itself. And the picture on the right is showing the translation. So we have a location table, which is a street address in string fields. Those get standardized into a way that a geocoder can understand that and turn those into lat longs. And those are points, and points are consequentially a geom object, which means once we do that, that patient location history or the patient location table is now interoperable with everything else that you decide to load, because the point and being as a geometry object in PostGIS without that functionality, we can do any sort of relations we need to. The other limitation is a common theme sometimes in OMOP of force one-to-one relationships that exist. And, person to location ID is the notable one here. Care site to location ID is another one, but care site or person to provider, there's a lot of them where just go on the forums. There's a lot of conversations about those. So our solution to that is just location history table. And the main point of that is to add temporality to this, right? The use case we have, people stay where they are their whole lives, but people move all the time, and we need to record that. In standard OMOP, you have person location, you have to pick one location, and there's no value of when they started or stopped living there. So the point of that is to be able to track that temporality so that when we do these joins with these data sets that have start and stop times, we can accurately associate that information. I do have person ID as a column here just to make things simpler, but location history table is also applicable for care sites, which also move. The last piece is we don't have a domain for what we're talking about. This is a completely novel type of data. It is not clinical data by any means. It is its whole new thing. And for a whole new thing, we need a whole new table, which we decided to rename on Friday, I believe, for some reason. But that is the case for it. I'll show it to you in more detail in a second. But the details, the more important pieces are here, that it is a person, it's location, there's concepts for that start and stop time, but the easiest way to imagine that is it is the measurement table with extra provenance, and it's almost exactly that. We needed more information to persist the location history and these pieces to it, but the structure of it is the measurement table because it is just so flexible. And here that is. I'm not sure how well you can see that. There's some dots to go through, but there's type concepts. The relationship concept, that's a big one to figure out. Source concept ID, operators, again, just like a measurement piece. But I'll just go through as Andrew illustrated earlier. Without this location history piece of it, we can't really get to this external exposure unless we're going to keep things static for these use cases. But this is our instance of the CDM. The blue is within the CDM. And it's a good point to make of this entire infrastructure that we're referring to in Gaia is distinct, it is separate from the CDM. It is a mechanism to which populate the CDM. But if you're sitting there thinking, well, I don't know if I can load all these things on my specialized database that has these restrictions, we understood that, and that's why it is this separate entity to which provide that data. And I'm sure Jared will mention his excellent work in containerizing all of this, but the idea would be as easily deployable as possible. And really not that many changes to the CDM at all. The ability to track temporality and the ability to take these place-related attributes and have them as a person-centric attribute. And how am I doing on time? Wow, I am flying. All right, so I put this in here just in case. To give a different perspective of how we arrived where we did, to make this make a little more sense. So again, leaning on the OHDSI mantra of steal, don't invent. We stole from OHDSI, so stole a couple times over. But we wanted to create extensible and reusable tooling, so we don't have to do this manual effort every single time for every different data set. And we have done that historically. N3C was a large example of that. To do that, we would need a common data representation to serve as that foundation. And what we arrived with was the geom and attribute. So I covered two there. So in order to enable both efficient processing of large volumes of data, but also have this static core functionality independent of formats. That's what I was referring to with this templating structure of we keep these things separate. They're treated the same. Our queries in the past iterations and other efforts that we've run into, every time you add a data set, you need to adjust your functionality to that, because a lot of times in GIS work, they'll keep that same source format to some extent, and there's customizable and extra work for each data source, and we want to make this as extensible as possible. So that was the route we went with that. Maintaining source data provenance and versioning, that was the metadata tables. Perhaps we'll split them up someday, given they are so loaded. They are both our main identifying structure and the core of all of our functionality. But as we stand now, the data source and the related variables to those data sources contain all of that. So versioning, provenance, and importantly, UUIDs. These catalogs that we are creating, we want to have these problems solved once. And when we have a record in the data source, which gives you these configurations, we have unique identifiers on those so that we are talking about the same thing. And as a community, you can slowly build these over time. We want to automate the process of data retrieval, ingestion, and standardization. Again, that's where we got to the extended part of these metadata tables. And it really is, I don't think we're going to go too far in detail of what the functions are that are inside of Gaia Core, the R wrapper essentially. But the level of dependencies and automation, notably Kyle has worked on, who's on this call, you can load a data source on its own with a function as simple as load data source with that ID. You can say load all the variables from that with something. You can say load a single variable that will then go download all of the dependencies you need, load the geometries that it needs, build the foreign keys, then load that single attribute, and then do it again for whatever else you'd want to do. There's a lot of flexibility and a lot of automation. And so again, it's this paradigm shift of we're building configurations, we're building a catalog of these recipes to automate all these different pieces of it, and along with the work that Pauline is doing, making it incredibly interoperable, both in terms of how we're doing on the vocabulary side, but now that we're working in the geospatial world, the interoperability there is another huge opportunity, and really helps with everything we need to do. We don't need to translate and create different routines for everything between locations and polygons or anything in between, because that's all handled as part of the classes in which they exist in PostGIS. And in order to enable that collaborative development is to build this catalog. It is a little burdensome to create these. You get in a role sometimes with it, but the idea would be to have helper tools and create an ecosystem that makes it a lot more feasible to grow out this catalog. And as we do that over time, things get easier. There's the potential that Tim's going to talk about in other cataloging metadata systems to even automate the generation of these configurations based on existing standards as well. So we're exploring what we can do, but so the sky's the limit for the types of data we can put in there. And again, when we say place related, it's just anything you can put on the globe, even if it's just with an identifier. And then the integration with OHDSI, clinical data and tooling, as I mentioned, the GIS extension, which is really quite simple, temporality, and a place to store person-centric versions of place data. And that, I believe, is all I got.
Okay, so to give this a little bit of a context, like I say, making a map is easy, right? How hard can it be? We have Google Maps, we have all this data that a lot of various governments all over the world are providing. Must be easy to pull this down and just attach it to our data, right? And this is kind of a very common misconception, I think, in the analytic world. So we're going to go over this a little bit and talk about how a catalog that's very carefully curated can help solve this problem. And this is kind of what I want to talk about for the next few minutes. But really, I don't know if you guys have heard of the FAIR principles, the findable, accessible, interoperable, and readable. And this is all about actually about machine actionability. It's not necessarily about humans finding things, right? It's about machines finding things and using it. This goes to what Robert was mentioning, that perhaps we can automate this in the future. And I'm showing some census data here. Census data should be easy, right? Has anyone actually gone and tried to get census data? Not the SVI stuff, but actually go to the census website and get the variable you want. Oh my gosh. And it's not just the census, right? That's not the only thing we're interested in. We're interested in a global, perhaps a data set that's outside of the United States. We're interested in things that are not related to the Census Bureau, perhaps the Environmental Protection Agency or NASA or a European agency that's sharing data of some nature. And it always comes down to the fact that we're getting from various different things. And these agencies are doing a wonderful job of building their own catalogs. But to do any analytics, we need to bring from several catalogs into our own catalog to make it useful within this kind of tool set. And I think this is kind of what I was getting at. And this is now temperature data instead of census data, and bringing these two things together. This is also raster versus that discrete vector data. How do we bring these two things together? These are generally very hard things to solve. And a lot of people have been doing really good work. And I really want to kind of draw your attention to the two top ones, Open GeoPortal and GeoBlacklight. One is out of Stanford and one is actually out of Tufts, correct? The Open. Yeah, the Open GeoPortal, and they've been building catalogs, but it's largely around downloadable data and historical data, which is not necessarily a bad thing, but particularly GeoBlacklight was built around like historical maps, like actual scanned maps, which is cool. And it's all thinking about how are we going to build these catalogs of geospatial data. And then I just threw up some of the agencies in the United States that are doing just amazing work, but they all build their own catalogs. And so there's still a lot of different sources that are not harmonized, that we have this problem still, that we have a problem with, and that the data is still a download, that we can get it. It's not actually a service that we can just plug ourselves into, although this is changing slightly. And then I want to just suggest this is a tool that I've been working on. We're calling it Geospatial Digital Special Collections at the University of Miami, that we're trying to solve some of these problems of bringing together catalogs from various different sources into one place. And it's been greatly, this group has really guided a lot of my thinking on that, and we're starting to connect these two things together. Go forward. Okay, so this was just, the whole idea is to meet these principles and also provide data as a service, so that you can basically go through the catalog, grab things, and then it's all there ready to plug into whatever tool. In this case, the OHDSI toolchain, the OHDSI toolchain, excuse me, as a service. And it was kind of like what Robert was talking about. It would be somewhat separate to the actual internal things that are behind a firewall that were being talked about, but that it would be connected to it directly as a service. And this is just an example of what the current collection looks like, and I just wanted to show it. I do have some links later. We only have 113 data sets in it right now, and of those, there's only a couple that are actually connected to the tool chain that we're talking about today. But one of the things I wanted to point out was this was built as a cloud native set of services. So this is a schematic. If you want to know more about this, I'd be happy to talk more about this. But basically, we're building metadata in an Excel file on Box. I really appreciated that one of the posters was doing this yesterday as well. This is for ease of access, so I can get my students just to enter metadata in. And then we can connect that to an administrative control plane on Kubernetes, and then just implement the entire set of services as a set of cloud native kind of things. We're working on actually deploying this through Helm, so that you could just download a Helm chart and then deploy it on your own cloud native infrastructure that you're dealing with. Like I say, I'll be happy to talk about that more later. And this is more what it really looks like. instead of a complex diagram, that we have students entering data on blocks. It goes through a Python thing that generates a bunch of shell scripts that feed into the geospatial data abstraction libraries, GDAL, which is an extraordinarily powerful tool for ETLing things into PostGIS and then providing these services out at the other end. But to do this, we need a lot of stuff. And this is what Robert was referring to in his presentation. And what I think is really important here is that within the Gaia toolchain, we've really focused on the last two, the ETL specific metadata and the administrative metadata. And I'll show what I mean by that later. This is the functional metadata, as we so-called within this group. And then we have a whole lot of other stuff that's kind of what we refer to as non-functional metadata, although I could argue with why that's not perhaps a good term, about citation, about provenance, and about other things that we need to keep track of if we want this to be a really good catalog. And I have these icons on the side here because these are things that we're building on. These are very standard ways of representing things on the internet. And a lot of work has been going into representing things on the internet for about the last 2 decades. How do we actually build metadata around objects on the internet? And this is building on that work that's been going on for a long time. You'll hear a lot about Dublin Core, schema.org, and then I'm really excited about the DCAT kind of vocabulary for describing things. This is not an OHDSI vocabulary. This is a GIS vocabulary or a metadata vocabulary. And the DCAT was recently, it started in Europe and was recently adopted by the US government as the way of representing data here as well. So it's kind of exciting to see that coming forward. And then I want to just add in at the end here that a lot of this is building towards this fair idea, but of machine actionability. It's not about human findability. It's about machines being able to go out and find the right data. If we describe it correctly, the machine go out and find the right data and actually pull things in through these catalogs kind of automatically. I want a map that shows heat exposure in Miami, and it'll go and find it for you and just get it for you. This is kind of a pie in the sky thing right now, but I know there's of people doing really good work on this, and this machine learning commons is one of the groups that's doing that. So the whole idea is that we take these existing catalogs, we move it through these vocabularies for metadata, and then it goes into the Gaia core. In some way, that they're somehow related. And Robert mentioned that the UUIDs are really important in this, and it's a nut that we haven't cracked yet. How are we going to represent things so that they have one unique ID? We have DOIs for our articles. We have DOIs for data, but those DOIs for data tend to go to landing pages, not to actual data sources. And we need to figure out how we're going to do this still. That's kind of a problem that we're working on, not necessarily only in this group. And what I wanted to share for the next few minutes was what this might actually look like. So this is the common Dublin Core kind of set of elements that we work with. And when I say we, I should warn you guys, I have a background in geography, but I have a joint appointment with the libraries and with our high performance computing center at the University of Miami. And so when I say we, I'm talking about librarians. This is librarian stuff. And we need some librarians in this group. I really see that need here, where we need to start thinking about this, because this is the non-functional metadata. But holy cow, if you're going to do a study and you're going to reference some data set from somewhere, you should be providing the correct citation information for that. And this is what really is there. And you'll recognize a lot of that stuff. I think really important this too is the licensing metadata. We often don't think about that, but as we move forward into a more data intensive world, we really need to pay attention to the licensing metadata on this. This is more of the GIS stuff. And you'll notice that we're talking about the data structure. It's that vector data structure. Even within that, you can have points, lines, or polygons. And then you have the Does everyone remember from my previous introduction what 4326 means? This means we're working with a spherical coordinate system with latitude and longitude. So it's recording that, the suggested scale of use, because oftentimes discrete points, you have different data densities and you need a suggested scale of use. And then we have a bounding polygon. This is just represented in what's known as well-known text for a polygon of lat-long coordinates. And then there's some other stuff there that is worth, and you'll notice that there's two more that are for raster only that I haven't included there. So we have these two sets. And then we have this variable level metadata, which I think is perhaps the most important right now. And I think it's still very much a work in progress. And you'll notice that I'm now working with the case study of the PM 2.5 data. And each column or each attribute gets its own metadata description so that we know what's going on. I think most important for our case study today is that we have the start and end date. And you may or may not recognize this is the same concept ID that Jared was showing in his work, and that I think you showed it also as well. No, it was Jared who showed it. And we have at the very bottom a linkage into the Gaia catalog. So what I've showed you right here is largely around this idea of the GIS catalog, the Geospatial Digital Space Special Collections I'm working with in Miami, but we're starting to include this connection into it so that we have all this non-functional metadata in this one catalog that connects to the functional metadata within the Gaia catalog. And I think there's a lot of work that's going on right now in this space of describing attributes within GIS. It's something that is very much a very active field right now about how we're going to do this and how we're going to share this data. And then this is what I think of as this is like the ETL stuff. This is what Robert showed. This is the kind of the metadata that Robert showed from the Gaia catalog, where we know what's going on. And he went much more into detail than my simple description of what's going on here. But this is what's in the Gaia catalog, and it's connected through that ID. And then I think the last thing is the administrative metadata that's also very important about who did this, when was it last updated. We're starting to build in some checksumming in our version, and I think we should build it back into this so that you can at least verify that you got the right data from the right source and it's not corrupted, and any update dates. And this is something to think about. Some geospatial data is very static. This was the value on this year. It doesn't really get updated. But some geospatial data is very active. In other words, it's being updated once a day, it's being updated once an hour, it's being updated very rapidly. So having this kind of information is super important for whatever we're doing. This was mentioned. I don't think I have this open right now, but hopefully this is recorded and maybe this will open. We have a very nice way. I don't need to sign in. I don't think I. Oh, it's not. But can I sign in, Andrew? Okay. Well, then it's going to ask you to do something on your phone. So this won't work. I'm going to go back. Okay. Yeah. I don't think so. But what I wanted to point out is that link is there. I should have made a QR code for it, perhaps. But there's and this is what Robert was talking about. It's complicated to put all that data in. I have students putting that in right now. We'll identify a data set in this group, and I'll ask my students to go ahead and create that record for me. Go find all that information and put it in, and then we connect it back to the database. I'm doing that in Google right now, in like a Google Excel sheet. But we're trying to build these tools, and we have a tool built on GitHub. If you're interested in getting a data set in, you can visit that GitHub site, give us some really basic information, and then we'll help you fill in the rest of it. And we're not expecting you to go out and fill in that entire record for us. We're expecting to help you fill that and build this catalog together. I think building on the principles that, oh, I have a screenshot of it, of course. I was thinking about this, that it wouldn't work. So this is what it looks like. You just fill in some data here, give us some information about who is the main organization behind this data set, the year, the type, and we'll go and figure out the rest of it with you. So I was going to do a live demo. I may still do this. I have a computer over here. I have some backup screenshots made as well. But I'm going to walk over here and share this screen and see if it works. So bear with me for just a second. Let me see if I can just grab it from this computer. I say share. I say this. I say, did it steal it from you? Oh, well, you should be able to see this now. And so if you go to the Zoom meeting, so we're sharing, we're just not sharing here. If we go to the Zoom meeting, we should be, there we go. Okay, wow. So this is actually almost working. So this is kind of what the catalog looks like right now. You'll see that, like I say, there's a bunch there. We are building this OHDSI GIS collection here. We have 3 things in it right now for this use case, particularly the PM 2.5 and some social vulnerability data where we've done it. I think what is really neat here is that I could know a concept code for a variable like PM 2.5, and at this point search for that concept code, and it'll come down and it'll tell me which attributes have that concept code in it. I can go into this data set now, and it'll actually highlight all the attributes that are it highlights the concept code that's here, so you can see what's going on. So it'll be a relatively easy way. I could also do any kind of full text searching for, instead of a concept code, I could do just PM 2.5, and it will be kind of it's perhaps a bad example that that you could do this, but it'll show up the same thing, the same attributes, and it's now highlighting PM 2.5. If I want to actually load one of these, I think this is where my live demo might break down, but I could try one, but I think I tried one earlier and it broke. But what I wanted to say is you would just click on one of these, and depending on your internet speed, and various other things, this will eventually turn green, and you would have that into the ETL that Robert was talking about. And I can just skip over here to this because I've done some. So this is we're now in PostGIS. We're using a DB manager that we have. We know this came from NASA CDAC. It has the attribute and the geom tables that Robert was talking about here. You can look at it. You can do a very nice query that I have up here that you probably can't see very well, but basically we're doing a join between those 2 tables to get a set of records of the actual polygons and the data. And then I move into QGIS and I can do that same query, and we end up with the map that is that Jared showed at the beginning. And I really like doing this as a GIS person. I think exploring the data is a really important first step of kind of taking a look at what's going on. So this is what we're looking at in our use case. As Jared mentioned, it's these polygons around cities that have variable or values attached to them. And if I look at one of these values, I can see that it has all of the years. Actually, this will only have 1 year attached to it because I did 1 year join, that we have the value as a number for this, and this is the 2010 version of it. But we could attach more years to it, and for the use cases, exactly what we did is we attached several more years to it, and we have it all kind of there. Let's see. I think, and this is just running that same query in QGIS. It's a wonderful tool that connects very well to Postgres. And I don't know why it's showing. Go away. Why it's showing all red like this, but it's a. I know why. Whatever. No, it's because I have the thing selected. Anyways, I just wanted to show this. This is about as far as I wanted to go with the live demo, is just showing you how that works and how it connects in. So I'm going to stop sharing over here and wander back there now. And then I want to close this with just, so we went through kind of all this. It turns green eventually, as you'll see on my next slide, if it goes. That was my attempt at a spinning yin yang, by the way, but it just didn't work. We went through all these. And we went through all these. And the way I want to end this is with a brief conversation about where we're going to go in the future with this. As someone who came into libraries as a non-librarian, I think there's a lot of really interesting directions this can go. And we've been working with some people to build JSON LD representations of these catalogs into the landing pages for those data sets. And then somehow make it so that some of the principles behind this are that that you would build local collections for whatever you're doing, and then we would be able to federate those metadata records so that other people could use that somehow. And the JSON LD would be kind of the lingua franca to be able to do that, and we would somehow manage to do that. This is kind of all in the future. Both Robert and I have mentioned this tool to ease metadata free, working on that and these standard IDs. I think there's a lot of stuff we can do here. I really want to have it so that you can just click on a bunch of data sets, have it all kind of stored like in a shopping cart, and then just say go, kind of like you're on Amazon.com, but you want to get data. And then have some tools to enable that visual exploration. I think it's a key important part of it that, and we're working on this at right now, that that we're building out some of those tools right now, so it would be all part of this containerized environment, so you could just click and explore as you go through the catalog and kind of see what's going on. And then finally, I want to end on this. With that linked open data, that JSON LD, we can start those kind of visualizations of the metadata through a set of triples that you can create with the JSON LD. And this was a visualization created by Doug Phils, who's been working with us, and it's a visualization of actually the attributes within the collection. And then I think this next one is even more interesting. This is a network visualization of the keywords. So you can see that our collections are relatively well kind of organized, or they have a lot of connections, but there's some outliers that you can see kind of off in those islands. And I think those are literally islands. I was working with a researcher on health risk in Trinidad and Tobago, and I think that's the piece of the collection that goes there. And I think that's, oh, and then this is the super cool part. So Doug is also really into the H3 representational network for indexing geospatial data at a global level. This is coming out of Waze, I believe. This is their way, or it's maybe not Waze, but Uber. And it's a way of indexing things so that we could do a spatial search. So you could basically draw a polygon and say what data sets are available here, and it would be able to do that. And this was a very detailed description of kind of what that JSON LD looks like. And it has kind of the polygons are on the left, and then it has a snippet of the variable level stuff on the right that you can see there. And I think that's it. I left a bunch of these for people to go to. This is the OHDSI GIS GitHub that we've been referring to. You can find that data from that site. You can find the place to add a data set or to request a data set. And then these are two of the ones that I've been working with the catalog that exists and the set of collections or repositories for the geospatial digital special collections. So I think I'll end it there. Okay, hi everybody, welcome back. You're going to get another half hour of me, and then you get the more interesting things for perhaps this working group, OHDSI. And what I'm going to talk about for the next few minutes is about geocoding, how we actually do this process of assigning some kind of geographic information to our patient data. And I think I'm throwing up this definition right here, just because I've heard at several points throughout this conference that geocoding might be the attaching of perhaps census tract ID to your patient data. That's, for me, from my perspective, that's a second step after geocoding. That we take the geocoding is actually attaching some kind of latitude and longitude or some kind of coordinate to our patient data, and then we would do some kind of spatial join, like I showed in that first slide or the first part of the presentation, where you attach it to a polygon. So I just want to be very clear that when I'm talking about geocoding, I'm talking about attaching some kind of latitude and longitude to something, or location to something. And it kind of fits into the common data model, the OMUP common data model. I think there's plenty of places where we can fit it, and we've mentioned several times already. I think Robert mentioned this, that we're thinking about a location history and a location. This is where these things would end up within the common data model. And then this is what I want to talk about a little bit today, about different ways of approaching this, things that we need to think about, particularly for privacy and for cybersecurity around this, and then go through some tools that we've been using, and walk you through a process basically for the case study that we've been talking about today, and showing you some other things along the way. And this is borrowing from Robert's slide. I just want to bring this back in, that the geocoding takes place outside of the common data model, and to a certain degree outside of Gaia, but it's a process that takes place outside of your normal instance of the OHDSI tool stack. And there's several reasons for this, and we'll get into that a little more. The other thing I want to talk about right at the beginning is there's several ways to do this, and it all depends on what your final goal is. When I think of geocoding, and in my experience, it's mostly about attaching some kind of lat long to an address. But that's not the only way to do this, and I want to make this very clear. And in our case study that we're doing today, as Jared pointed out at the beginning, we're working with city-based locations at a very international scale. So depending on the scale of your study, you might want to do different ways of approaching it. And I'll get into why this is true. The best way to do it is if you have the parcel level data. That's the best way to get accurate geocoding information. Match the parcel to the address. If you don't have that, then you go into what's called interpolation-based geocoding. And this is where we find a street, we know its beginning and end addresses, and we interpolate along that line whereabouts the house might land, based on its address. And then I think a lot of people in this room and in this community are familiar with zip code based geocoding, where you have the zip code from your patient data and you want to use that as your location information. I would push back against that as a geographer. I know it's very common in this community. The problem with zip codes is they're not actually polygons. Zip codes are routes. They're postal routes. They're literally the route that the post person drives, right? This is a zip code. It's a line. It's not a polygon. And zip codes change all the time. They change like every 6 months. They get updates. And maintaining that kind of stuff against census tract data, which is what most people are interested in, or some kind of polygon-based data, it's actually problematic to do that crosswalk, and you lose accuracy on your information. You can do it, yeah. People ask me to do it, and I'm like, well, are you sure you want to do that? So just thinking about that. And then what we did today is city-based, or you could actually go check your houses, which might be a little creepy. But I wanted to make that, and this all goes to scale. In geography, we talk a lot about scale of analysis. It really depends on your scale of analysis, what you're trying to do. For most of the people I work with at UM, within the School of Medicine there, they're thinking about the county scale. So we do address-based interpolated geocoding. And then, like I say, we're doing something slightly different today. But I think what's really important in all of this is that for the work we're doing in this group, we need lat long coordinates. We want to be able to do those spatial joins, because we're not only interested in census tracts. We're not only interested in this one set of polygons. We want to get, temperature data. We want to get air pollution data. We want to get all kinds of stuff and be able to do those individual joins based on those lat long coordinates. I want to just throw this out here because this is something that we do in the libraries. I'm a librarian, I'll remind you. We like attaching location information to all kinds of stuff, including text. You know, a text mentions a town. Can we geocode all the towns in this text? Well, let's try. And we do it using a gazetteer. GeoNames is one of them. A gazetteer is just a list of place names that you can match and do fuzzy string matching against. And that gazetteer will return a set of lat long coordinates for that place name. And so we can do this for cities, and this is basically what we did for our case study today, is we have a bunch of city location names within that PM 2.5 database that Jared described, and we could then match XY coordinates to those city locations. And OpenRefine is a wonderful tool. If you don't know about it yet, it was put out by Google a while ago. It's a CSV data cleaning tool. It's really good with fuzzy string matching and all kinds of other stuff. It's just a good way to clean up messy data. So this is just one example of how you could do it. And this is what you get back from those gazetteer geocoders. And of course, the most important thing are the Latin long that it gives back. And well, I think I put it here actually. It returns WGS 84, right? So it's returning these lat long coordinates based on this global center of the Earth. You do need an account name, but it's not actually anything other than that. So the next thing I want to talk about is once you've kind of decided on your approach, what kind of privacy concerns are there? And I put those two questions at the top, and Jimmy and I have been having a long and interesting conversation around this. Can you send de-identified addresses to a web-based geocoder? And in other words, send your data off premises and get the lat longs back? I don't know. I'm not a lawyer, and I am not incredibly compliant, or I don't know a lot about HIPAA. If you want to say something, sure.
Are you asking me, or is there somebody else in the room?
No, there's someone in the audience. Just a moment.
Oh, okay.
So I think on a previous slide, you mentioned something that made me think, yeah, we can't do that. We can't put on the web our data. What we're trying to do is constructing synthetic databases. This is my colleague here that works on that. Because, yeah, we're custodians of private data and we can't do that. But then I was thinking maybe an interesting way to deal with this is once that kind of information is geographic, because what we have a problem with re-identification is if we study like even moderately rare things, rare diseases, if you say in this census tract, there's this person with this disease, like the possibility of re-identification is very, very high. So maybe it's interesting to move away from the individual level analysis and do aggregate analysis. And the unit of study would be the census tract and be kind of the prevalence of whatever in that space.
Just briefly going to comment. I think our safe assumption is the safest way for most healthcare data in most institutions in most parts of the world is to download the data, do your geocoding locally rather than send it to the server. So I think that's in general what we endorse in the work group. And so there are other methods. I think probably want to concentrate on one we know is safe rather than the questions about the ones that are maybe not.
I agree with that, and I think that's you basically described the problem very well. Thank you for that, and I agree 100% with Andrew that the safe side is the better side. Although I'm very curious about this conversation as someone outside of this workspace as to what can be done. But I think I skipped ahead somehow. So you were talking about the re-identification risk. This is exactly what we're worried about those low number studies where you could potentially re-identify someone. Notice that this is on the analytic and when you're publishing on this is where you have to be extraordinarily careful, if you ask me. You know, you've got your geocoded data, you've done your analysis. How do I disseminate this without breaking rules? That's where it gets really, you got to be super careful, no? Because if you publish that map with that census tract colored by that and say this is this disease, problem, right?
Mm-hmm.
Yeah.
So I would ask, or whoever was the speaker regarding the synthetic data question, that comment. Thank you for bringing that up, because oftentimes before one can do any of this, obtaining the personal identifiable information and addresses, before you are transforming them into lat lons with any of these software, often people have to engage the question about spatial unit and the spatial unit of analysis. And this has to do with like, what is the ethics review? What is the ethics review board going to say for these things? The IRB, right? What's your scope of research? What is it that you actually are going to aggregate it for some population level question? Because individual level information at latitude, longitude has a specificity that is in the privacy disclosure or risk re-identification, like it's often unacceptably high re-identification. But on the screen here, there is that, what if we had like de-identified addresses? What is that as a, potential avenue to like minimize the risk? I'm going to put it there, but ask this as like whoever is the recipient. I know we have to move on, but what is your organization or institution's policy on this? Do they have a policy on it? Because that can also guide your decisions on whether or not you can say a yes to that first question.
I think that's a real important point. And I know at UM that we have a policy where as long as it's been de-identified well and people are aware of the re-identification risk in the pipeline of dissemination and analysis, that we will do it. But different institutions have different policies, and I think that's a real key. And then I am going to move on, but I'd be happy to talk more about this later. The other thing we mentioned that we're doing some containerization in this work, and there are some cybersecurity concerns if you're going to do this in a containerized environment at all, even if it's local, because we know that some of the open source software and some of the containerization things have security holes in them, so that if you were ever to do this, you need to be aware of this. And Jimmy, I don't know if you want to say something, but you've been doing some wonderful work kind of trying to vet this for a moment.
Yeah. So whether you're dealing with open source software or premium software, so let's say DeGauss, PostGIS, or Nominitim, or ArcGIS, any of these software, often to have that installed locally, you still have to engage the question of like, is this software secure? Does it have any holes? Does it have open ports? Does it make API egressing to an external server, right? So for some software, they have like a cloud enterprise. So when, like say ArcGIS Pro, you're actually pinging that, and if it's not pointed towards your local installation, it's pointed towards their cloud enterprise. And so there's then that question of what then goes along with the query. What is the IP logging that comes along with the entire series of addresses you might be geocoding? Thereby, there's like a mapping. And then if the data is going to flow there, how long does it stay there? And for some software, some business associate agreements, there's often a data deletion clause if there is like some retention for auditing or archival. But if there's a intention that like this has to be deleted in 30 days, right? That you need that for security review.
And I'll let everyone in the room know, and everyone in the virtual environment know. Jimmy and I have wonderful conversations about this. If you want to join the conversation outside of the context of this presentation, we'd love to have you. I think there's a lot of things to think about here that are really interesting. So we made a little grid here of HIPAA compliant geocoders so there are HIPAA compliant geocoders out there, and you'll notice Jimmy mentioned a couple of them at the top. ArcGIS Enterprise is one of them, but note the kind of disclaimer at the bottom that all the HIPAA compliance is as per the vendor's claims. once again, I am not a lawyer, and I would treat that at your own risk and go talk to your institutional people about that. And we're going to go through these top four kind of for the rest of the day. The ArcGIS, the Nominatim, which is the OpenStreetMap geocoder. It has a global coverage in terms of kind of global studies. DGAUS is a very nice geocoder that you can download and install locally. It's US only, unfortunately. And the PostGIS Tiger is Robert mentioned the Tiger files. The Tiger files are the U.S. government's line file data set of the United States, which includes streets. I can't remember what Tiger stands for. Something geospatial something. Right, but PostGIS works with Tiger very well. Those are the government files from the U.S. government, but they're U.S. only as well. So this is where I wanted to go, and you'll notice that some of these are proprietary and are somewhat expensive, and some of them are less. And we can come back to that. Yeah.
So a lot of folks here are actually not from the U.S. I would say most of the folks in the room, for example, are not from the U.S. So you just maybe underline a little bit about how international approaches are going to go.
Great, thanks for that. So note that the example I gave a couple slides back using the GeoNames geocoder is an international way of doing place names for international locations. And Nominatim, I've become a huge OpenStreetMap fan. OpenStreetMap, for those of you who don't know, is kind of like a wiki map of the entire world where people can contribute to it. They start with government files for everywhere and then let people build on it. I have become a huge fan. It's an enormously valuable resource. I've heard it termed one of the most valuable resources moving into the future. Even Google uses it. Know that they use this OpenStreetMap, Nominatim, same thing. Oh, I wanted to just throw this for the fun of it. This is an old slide that a data scientist friend of mine showed me a long time ago. You know, I think we could very easily cross out some of these terms and just put GIS technician and spatial analytics into here. That we spend most of our time data cleaning, and when you come to geocoding, this is the difficult step. There is no doubt about it. That as you prepare your data, once you've kind of decided on your scale and you've decided on your tool, your next step is actually to get ready and do your data. And I can't say enough about the top line that you should do all this, even if you're using on-prem disconnected computers, whatever you're doing, de-identify it before you're doing your geocoding, just in case you don't understand that process. And what I mean by that is patient ID or some kind of ID with just the address and nothing else. No other data. It'll make your geocoding process special. Oh, the camera's following Andrew now. And then we're going to get into this cleaning. So most geocoders need, if you're going to do address, that interpolative geocoding process, you need the street number, the city, the postal code, and other things in separate columns. Oftentimes, this is not how your database people are going to give it to you. They're going to give it to you as one string. And I get this all the time that someone needs help with a study, and they will give me address data that's all in one line. And so you have to kind of separate it out, deal with it. Things that are perhaps not as to think about that you may not have thought about before. Abbreviations are enormously problematic. Street, boulevard, whatever. You need to somehow standardize these. This is where that OpenRefine really helps. You can use OpenRefine to standardize a lot of this stuff. And then you need fuzzy filters to catch spelling errors and prepare synonym dictionaries for official and common names. Like oftentimes a street will have an official name, but everyone who lives in that neighborhood calls it something else, including your patient who put their data into the system. So these are just some things you may run into. It's very locale specific, that every location is going to be different. And then that's kind of a reminder at the bottom. So this is a good example. And what I mean by that is it looks pretty clean to me. I have the address in one field, and I still have to separate that out a little bit. But everything else looks pretty good, but I don't have any of this. Most geocoders want this information as well. I don't know what to do with unincorporated county. The geocoder is not going to know what that means. again, the abbreviations Court Avenue. So there's even in this good example, there's two numbers. How does it know 52nd versus the actual street number or the number? There's all kinds of stuff to deal with here, and this is a real example. So this was something that someone gave me. Look at those zip codes over there. Yeah. What am I supposed to do with that?
I have committed
all kinds of.
I have committed the
Yeah.
cardinal sin too of accidentally treating zip codes as numbers, but they're not numbers.
You notice streets are abbreviated differently. Some have lots of extra numbers that I have no idea what the geocoder is going to do with. The zip codes, 218. Most geocoders want 218th. They don't want just a number. They want the ordinal with it. So there's all these kinds of problems. And the take home on this is actually for your IT folks. Whoever's putting those data in, before anything is attached to it, should be using a normalizer. The U.S. Post Office has a great normalizer. It's the one that says, are you sure you want that or you want this address? That's the one in the public database. Use that one. And then at a global level, this server, Melissa, will do that for you, but it costs money, unfortunately. ArcGIS, PostGIS, it doesn't. Well, that's a normalizer. That's not the one that will tell you the registered one on the. That's a different thing. Yeah. So we did a little bit of benchmarking that we wanted to share with you, and so we benchmarked. We spun up all these geocoders locally and tested them all out. And again, PostGIS and DGAUS are US only. ArcGIS Pro and Nomentum are a global level. And what I did for this one is I took 5,000 random addresses in Miami-Dade County with known locations, and then I fed them into the different geocoders. And I think what you can see is that these are the error thresholds, right? That there's that number within 0 to 100 feet. There's that number within 100 to 499 feet. Everything has error. Everything. In a geocoder, everything has error. And so something to think about, if I'm working at a tract level or some other administrative unit, does that matter? It might, but it probably won't. And it's interesting. Think about this next time you read a study that has some kind of geospatial data in it. Do they mention this? We should be talking about this as we disseminate things. Just pointing out a few other things. This was, in my case, I found Nomentum, the international one, had the lowest median. It found stuff great. I also know that ArcGIS Pro, which you pay for, is also very good. And it's because they both have really large teams of people behind them. One is a volunteer community, one is a paid community. And this is just an example of what different things look like. The original is the green. And the one on the left is showing house addresses. And you can see how ArcGIS geocodes the street, that DGAUS and Nomentum actually use the same database. They're using those tiger line files. And then that the Nomentum did the best. The one on the right is an address, an apartment address. And I wanted to show that because a lot of patients live in apartments. And you can see how the error gets bigger as you go to apartments. It's a problem. And then this was something that Jimmy did. He did an entirely different study. So I chose all residential addresses. Jimmy looked at institutional addresses, and it's a very different thing. And you can see that Nomentum returns several results that are kind of off, and that the PostGIS and DGAUS landed pretty much on the spot for those.
They're like overlapping, so
yeah.
they're very precise, but the Nomentum option, there was like some type of string similarities match that they couldn't find an exact one that was right at that same spot. It was up the street.
Well, I was going to say, the take home from this that I understood from this is that it's very locale specific. If you're working in a very small area, you really need to benchmark your stuff and check to see which one's working the best. If you're working at a larger scale, it gets less important. So it really depends on what you're doing. And these were just some other results that were interesting. So all except for Nomentum, unfortunately, give a kind of a rating of their match. So you can actually have a threshold, much like we heard about yesterday, where you could just throw out these addresses and say, they're not valid. Although why they're not valid, that what you're doing, I don't know. Nominatim doesn't have a match score, unfortunately. I know they're working on it, but they haven't done it yet. Notice how they're giving back different coordinate reference systems depending on what you're working with, and that you get either single or multiple results back that you have to kind of sort through. And this was just an example with dgauss. Dgauss is a wonderful tool. It's fully containerized, and it's a very easy Docker install to just grab it and geocode your de-identified addresses. And this is kind of what you start with. You set up your data correctly. You run it through with an input that's based on your ID that you give it, the address, the city, the state, and the zip, and then it spits back these lat-long coordinates, and then you have to kind of decide what you're doing with that at the end if you're going to take into account any errors or accuracy considerations. And then I think this is almost our final slide. These are just some considerations to think about as you think about this. Some of them are larger than others. Both PostGIS and Nominatim are fairly large installs. They take like a day and a half to install. They're not simple installs. You're going to need help with this. But you can choose by region. And what I mean by that, with Nominatim in the international case, you can say, oh, I only want Europe, or I only want Asia, or I only want Australia. And you can kind of lower your install requirements on that. Let's see, what else was there? Oh, yeah, well, subsetting, exactly. And then whether you can containerize it or not. Yeah, go ahead, Jimmy.
So I'll add to the Nominatim and PostGIS. That component is just the amount of spatial layers and parcel information captured. They just tend to be, it's decompressed. They get to be quite large. But for, let's say, the United States and territories, so often people don't remember that sort of component to it, where it's not all just North American continent. So some of these other areas, even though it might be North America, sorry, the territories, they're not part of the continental US. So you often might need to actually have a different region for Nominatim to be able to find them. But for PostGIS, it's the same thing. You have to assemble the spatial layers for each place, but sometimes you can make it state by state, and it doesn't have to be like 233 for the entire continent. Yeah, it could be much smaller.
Great. I think this is where I'm going to leave it and just say, we are planning on building this into the pipeline right now. As Robert mentioned, that it would be part of this pipeline that you could install, but it's still kind of a work in progress, and that, we'd love to hear your thoughts on this and for you to join this conversation.
Hello, everyone. So let's talk about vocabularies used for representing geospatial data, particularly GIS vocabulary package. So I'm Polina Tolapova, and also with Jared Hatelin, we will tell you a bit about this work. So first of all, the purpose, just let's recall this. The purpose is elevates data-driven healthcare research by integrating various data, especially spatial, environmental, behavioral, socioeconomic, phenotypic, and toxin-related determinants of health. So key benefits of this work that it supports multi-dimensional analysis of health outcomes and accounts for both external environmental exposures and intrinsic patient characteristics. So this GIS vocabulary package expands the OHDSI to include external contextual factors and also facilitates the understanding of interplay between environment and health. So it was developed by GIS working group within OHDSI community, and package includes vocabulary, scripts, and documentation to support integration locally. And importance is quite clear, so it addresses the growing demand to incorporate societal and environmental factors into healthcare data research and provides integration with existing OHDSI vocabularies for enhanced data analysis. So the objective is to provide a comprehensive, standardized framework to incorporate all these data, geographic, toxicological, healthcare, behavioral, socioeconomic terminology, a lot of the data into the OHDSI. And it could be applicable by terminologists, ontologists, researchers, epidemiologists, and data analysts. So the integration feature that seamlessly integrates within the existing OMOP CDM. So everything aligns with OMOP standards, and it designs to adapt to evolving data needs and expanding global health context. The content of GIS vocabulary package. The package contains 3 sub-vocabulary. First one is OMOP GIS vocabulary. It's a small one for geocoding purpose. OMOP exposome vocabulary. It's a toxicant-related vocabulary that contains chemical substances inside. And OMOP SDOH, or social determinants of health vocabulary, encompass social determinants of health. Let's talk about each of them a bit. So OMOP GIS vocabulary, standardized geographical terminology and spatial data, supports geospatial epidemiology, healthcare accessibility studies, and population health research. So there are 159 concepts in the observation OMOP domain currently, and it focuses on geography, boundaries, and spatial elements. So use cases, it enables analysis of geographic health disparities and facilitates research on the impact of location on health outcomes. The next vocabulary here is OMOP exposome vocabulary. This one integrates environmental and toxicological factors that we called exposome into OMOP CDM. And it is a comprehensive taxonomy of environmental pollutants, toxins, and chemical agents. In fact, it's designed for structured data capture, analysis, and interpretation of exposomes. These concepts belong to the observation domain and also substance concept class in OMOP CDM. It's not a drug, but observation and substance. And use cases, it provides the foundation for toxicological studies in observational health data and supports research on environmental exposure and health outcomes. The third vocabulary here, last but not least, it's OMOP SDOH vocabulary. This one encapsulates terminologies representing environmental and societal factors that influence health outcomes. And this hierarchical vocabulary integrates standards like social vulnerability index, or data derived from Agency for Healthcare Research and Quality, or SDOH or ontology notes, social determinants of health ontology notes. And the key components of this sub-vocabulary, it's different elements or terms related to demographics, education, geographic location, physical environments, population, social and community context. So a lot of different components are there. And use cases, it enables multidimensional analysis of social determinants of health and supports studies on the impact of social and environmental factors of health. And here you can see the key data sources that we used to to assemble this vocabulary package. For instance, GIS vocabulary package, as you see, contains 3 sub-vocabularies, and OMOP SDOH refers to, for instance, social and environmental determinants of health, SEDH, or social determinants of health ontology, or area deprivation index, not or and. Also contains variables from Agency for Healthcare Research and Quality SDOH database. Also, there is child opportunity index and all variables related to this index. Environmental justice index, social vulnerability index is also there, and sustainable development goals as well. Talking about OMOP GIS, it's mostly vector features and literature review outcome, and OMOP exposome contains T3DB database, which encompasses the toxicants and toxin target, so it's quite known, and we integrate this database into the OMOP CDM format. So talking about the structure and concept management. First of all, there is very similar, not similar, in identical structure to OMOP CDM vocabulary tables or OMOP CDM vocabulary. So you will find their concept names. Usually they derived from source data or were created by the guidance from relevant literature. Then there will be concept codes. They are also adopted from the source data. It's like short names of the variables usually in these databases. or some of them auto-generated. Those which are auto-generated, they contain GIS prefix before the numbers in the concept code. Then you'll see domain and concept classes. So we introduced 7 new domains. It's a terrible for OHDSI community, I suppose, because they were, yeah, but they can be terrified. But anyway, we need these 7 new domains to classify all terms under the categories. And also there are 31 concept classes created to group and categorize these concepts using the vocabulary package. The next one is vocabulary ID, and there you can filter terms using OMOP.js vocabulary, OMOP Exposum vocabulary, or OMOP SDH vocabulary. Like vocabulary ID is equal to the name of the vocabulary you want to discover. Then concept status or standardness of the concept. So if we have the mapping to the OMOP, the concept will be non-standard. If there is no mapping, concept will be standard. Simple rule that is applied usually everywhere in OMOP. Also, there is valid start date, and these dates adopted from the source were relevant. If not, it was a vocabulary release date. And also, we introduced 5 new relationship pairs, and relationship can be found in the concept relationship table, in fact. And I will show you a bit later what are they. Let's talk about new domains. So first one is behavioral feature, refers to action or behaviors by individuals that influence health outcomes, often related to the lifestyle choices. An example, it's like element relevant to physical activity. It's a classification node that contains variables below this node. Then we have demographic feature, everything that is related to population, age, gender, race, ethnicity. The majority of these concepts are mapped to OMOP because demographics is covered by OMOP quite good. And example is race in population, for instance, but also there is just a race, not in population, like at the patient level. Then we have environmental feature. Here we have natural or man-made environmental factors that affects health and well-being. And example, air quality index. Next one is geographic feature, so it's clear what it should be. For instance, state, county, FIPS code, it's a geographic feature. Then we have healthcare feature, and for instance, one of the main nodes is element related to healthcare. So it would be classification node for this branch or for this domain. Then we have observation is a typical OMOP domain, it exists. Then another new domain is phenotypic feature. Usually it refers to observable trait or characteristics of individual influenced by genetic or environmental factors. An example is element relevant to depression. It's not a condition like a depression. It's element relevant to depression of the phenotypic feature domain, and it can contain additional variables below them in the hierarchy. Then we have socioeconomic feature. So social and economic factors that impact health. And example, employment in population. And the last one is a type concept. This one is also exists in OMOP. Just categorization used to define where the record comes from. It's origin of the records that we see in the OMOP, like air quality database would be the example. Then talking about concept classes, as maybe you remember, there are 31 concept classes, and I'm not going to discuss each of them, but there are some main categories of these concept classes. We have constructs, determinants, items, and item values. And talking about constructs, it's abstract or behavioral elements measured indirectly or subjectively, often through surveys or proxies, and constructs capture social, psychological, and environmental factors that influence health, but they are not directly measurable or causal. Examples, social norms and attitude, very broad construct, cannot be measured. Sexual orientation, occupational hazard, neighborhood safety. You see, the next one is determinant, a specific measurable factor. So if you try to find all determinants, it will be like concept class ID like determinant, and you will see all of them from various sources. The source is before, like a prefix before the category of the concept class. as you see here, SDOHO or SDOH, AHRQ determinant, or whatever. And here we have veteran status, healthcare provider availability, income, tobacco use, vaccination status, etc. Talking about items, they are specific measurable data point or elements within the particular data source that we used. And it used to evaluate larger construct or determinant. For instance, percent of household without a motor vehicle, it's ADI item, or all cost readmission per 100 male admissions. So it will be also item. Civilians age 16 plus unemployment estimate is SVI item, is also item. And item values is they are similar to values in the OMOP-CDM, for instance, employed, unemployed, self-employed, just values or retired, and they also derive from data sources that we collected. So we didn't create them by ourselves, we just collect them and integrate into the OMOP-CDM. And now relationships. So these relationships refer to different vocabularies. For instance, locates in cell and cell location, or locates in tissue and tissue contains. They are about OMOP exposome vocabulary. So they describe like certain agent or substance is found within or target a cellular entity. So you may find such a detailed relationship within this vocabulary. Also, you can see here not new relationships like MAPS2 or ESA. They are typical for OMOP-CDM. MAPS2 is just for equivalent mapping. ESA is hierarchical relationship that connects various nodes of our vocabulary with each other. Has associated findings also exist. His relative context exists already, and has geometry is a new one. Represents the spatial or geometric relationship between the entity. And now I would like to ask Jared. Jared, would you like to step in and tell about the OMOP.js vocabulary build pipeline that you developed to containerize the vocabulary package?
Yeah, absolutely. I just requested to take control. I don't know if you can accept the request or how that works. I think that lets me change slides, but
I can change them for you, or maybe
or you
Andrew
can change them.
Okay.
Okay. All right, I'll dive into it then. So yeah, so Paulina and the GIS working group, many others have developed, and it looks like I should be able to. Oh yeah. Anyway, have developed an amazing set of vocabulary terms, and I will actually share my screen then. Let me quickly do so. All right, can you all see this? Oops, that's not where I wanted to be. Okay, this is where we're at, right? Hopefully everybody can see this.
We can see the build pipeline.
Awesome. Okay, so the GIS team and Paulina have come up with all of these different terms and relationships and classes and domains to represent these various concepts across the exposome and the SDOH and the GIS kind of data realms. And what I have done is take that underlying set of terms in its current format, which is SESOM format. And I don't know if, Paulina, you mentioned this already, but it's simple standard for sharing ontology mappings. It's effectively a way of representing relationships between terminologies or mappings. So it's a data model that you can use to represent these types of linkages. And we've taken all of these different terms and the relationships in this format in a Google sheet specifically, where they've been reviewed and validated, and those get ingested into a GitHub repository, which then routes them through onto the cloud to a self-hosted runner that actually executes a bunch of logic against them to kind of mold and transform them into what you know as the kind of the OMOP vocabulary tables. So the specifically for, in this case, the GIS vocabulary, after which those tables get placed back into the OMOP repository the GitHub repository where they can be downloaded and then ingested into a workflow. So that's kind of the overview. I have a few slides to go through what that actually means. So this is, you all have probably seen a Google Sheet. This is data in SESAM formats in a Google Sheet. But what you maybe didn't know, and what I only found out somewhat recently, is that all of these Google Sheets and docs and forms and everything, they come together with some integration tooling. In this case, it's called apps script. And you can actually write in kind of a JavaScript type, they call it Google script specifically. You can write code that triggers on certain events or that triggers on a schedule and references your sheet, which is super useful if you want to take data that's in a Google Sheet and place it somewhere else. And so what we've done is we've set up a scheduled ingestion where these data in this Google Sheet every day or every time they get changed, or we can vary the kind of how often this happens, but they get then committed to GitHub. So they get sent off from this Google Sheet onto a CSV file that's committed and version controlled on a GitHub repository. And once they're in GitHub, and this is actually a public repo that you can browse to right now if you're interested, it's toughctsi/CVB for custom vocab builder. They get committed there, and then they're aligned with a GitHub action. So again, something that runs a process on those CSV files. In this case, it's actually a single CSV file. And it takes those data and it sends them off to a location where all of this logic can actually be affected on them, essentially. And so we have we've gone from app scripts to get to the GitHub repo, and in the GitHub repo, we can use a GitHub action to actually run a little pipeline, and that pipeline then gets sent off to, in our case, our Azure instance for Tufts Medicine, onto a self-hosted GitHub runner, which is just a little Linux machine in the cloud, that then can execute SQL statements against a vocabulary server. And this way, we can maintain a private server that then has all of the normal OMOP vocab, but then we can ingest and update our GIS terms in that same server. And so it's going to run this set of logic, and then it's going to validate that logic. And once it's validated and everything checks out, it exports the delta table. So everything that's different between your standard OMOP version at the moment and the GIS terms that you've plugged in. And it commits those back into the GitHub repository. So again, version controlled. Again, you can find all of these online. But then you have this set of delta vocabulary that we're calling that you can then upload into a database and combine together with the standard vocabulary tables and then use to actually run analyses. So you could download from this repo right now all of these CSV files, plug them into your database, and then insert them into the various respective tables. And now you have the GIS vocabulary in OMOP format that you can use to run a study or to do whatever you want with. So that's more or less taking this single data model, the SESAM representation, and going all the way through this process to get to an output of something you can use in OMOP. And so we've done that for GIS. And this is actually the set of tables is what Tim used when he created this awesome catalog entry and associated variable data for the PM 2.5 data. But this also then underlies a lot of the analytics that I'll talk about in the upcoming sessions. There's a couple more slides, and Paulina, maybe I'll just finish these off if that's okay from your sides. Just about the use case specifically. And so in the data set, there's actually a lot of different terms related to PM 2.5. In particular, we're looking, at least in this use case, we're looking at this annual average concentration of PM 2.5 in micrograms per cubic meter. And this is going to be the monitored value. So this is not an estimate. This is actually a value that's being directly measured via satellite imagery. But there's a lot of other terms that we could, in theory, expand this use case to, and bring in other data sets and things like that we would associate these concepts with. This is, again, a view on the external exposure table. Again, here, brief. I'm not going to go into too much detail, really no detail at all, but there's some columns that you should focus on here, or that are going to be relevant in the coming two sessions, which are the exposure concept ID. And this is really like this idea of the annual average concentration of PM2.5. You have the type concept ID, which covers provenance. In this case, it's either satellite imagery or an air quality database. It could have been either of those. Then you have an exposure relationship concept ID, and this is really how is the variable of interest related to this particular person or the location of that person. So it's kind of a geometric relationship that you're discussing here. In our case, it was within, because our geocoded city fell within this polygon of air quality value that we're using in our underlying data sets. And then the last two here, we had actually a standard unit concept ID for micrograms per cubic meter that already exists in OMA. So we just referenced that, and value as number is the actual value. And so I can kind of show you what I'm talking about more specifically here, but this is like a row of the synthetic data that was created for external exposure, where you're referencing this 2 billion plus concept created again by that pipeline. You're referencing an exposure type concept also created by that pipeline that's very specific to, in this case, an air quality database. You then have the relationship, which I already mentioned, how it's geometrically related to a given location, and then your standard unit concept ID. And then this 37.5 would actually be the concentration at that location for this person. So you have your location ID, your person, and then the variables and associated data with them. And this is only a subset of those columns I just showed, but these are the most critical relative to the vocabulary that we constructed. So, all right, and that I think is the last slide before I move on. So I'm going to stop sharing now. All right, so this next session, I'm going to talk a little bit about the containerization work and kind of this general containerized process that's been alluded to throughout the workshop so far today. Also, a quick shout out to Tim, who has really kind of pushed forward on a lot of the efforts here, especially with regard to the Solar and the catalog and kind of the integration with BroadC, for those who aren't familiar. Also great, Tim, that you showed the demo, because I can then refer exactly to what you were showing. All of that demo was done using some of these containers, or at least I think it was, because it was running locally on your machine. So I'll get into that in just a second. Let me go to my next slide here if I can. Great. So this is a figure that was made actually by Jay, who I think is on the call, or at least he was earlier, that kind of gives an overview of what we're talking about when we talk about the Gaia network, or the Gaia toolchain, or OHDSI GIS toolchain. A lot of different terminology being thrown around, but more or less it's a set of 6 containers that's, in theory, you could deploy locally, and as Robert was saying, kind of adjacent to your broader OMOP workflow. That will, at kind of their core, at their minimum, will help you take a location and a location history table from your OMOP instance, together with a set of variables of interest, be it a PM2.5 concentration, or social vulnerability index, or any other set of these GIS variables, and combine those things to produce this, what we're calling external exposure. So this OMOP extension table that has a person, a place, and a variable of interest together with a period of time, so that we can really have this kind of spatial temporal link with a value or some variable that we're interested in studying. And so these containers help deploy and facilitate that workflow on a lot of different environments, be it on your on-premise environment, or your local laptop, or your cloud environment for your institution. You can deploy this in a lot of different places, in a relatively straightforward manner, I should say. For those of you who aren't familiar with Docker, think of it as a small computer running on your computer. It's a little isolated computational space that you can run a very distinct or defined process, and you can share that kind of computational space with somebody else, and they can run it and expect essentially the same environments to be available and then to run in the same fashion. And so it's very useful for extending deployments and bringing up software on Mac versus Windows versus Linux or the cloud. And you heard Tim already give a nice explanation of Kubernetes, and that's a whole other thing that I'm not going to go into today. But in any case, those are the 6 containers, and I'll get into a little bit about what each of them do, although most have been referenced. So Gaia Catalog, this is, if you think back to Tim's demo, this is really the web application or the interface that Tim was using, where you could search the concept ID or search PM2.5, and it would return a list of possible hits. So this is more or less a web app that allows you to browse data sets that you have available or that have been made available elsewhere, depending on how you configure it. But it's an interface to what types of data that you could potentially link with your OMOP data, if you will. Then we move down and we have Gaia Solar. And Solar is more of a utility container. It facilitates a much quicker search. So if you notice when Tim was showing his search demonstration, it was very quick to actually run through that data set. And that's because Solar had pre-built an index that allows it to very rapidly parse through a bunch of data and find terms of interest or hits that are, let's say, quality matches, if you will. So Solar is facilitating a much more rapid parsing or searching of this kind of rich GIS catalog or Gaia catalog. Then you have Gaia KG, which is still, I would say, in its early stages, but it's at least in terms of being part of the broader Gaia container framework, which itself is actually pretty new. But this is kind of, if you think back to the knowledge graph slides that were on Tim's presentation, this idea of linking these different catalogs or different kind of catalog entities, if you will, and the concepts and things that they represent, being able to kind of visually explore what data are available in the GIS and kind of broader catalogs there. So it's Gaia KG. Gaia DGauss is specifically the DGauss geocoder that was talked about, that Tim gave a very nice overview of. I should also say, in a prior iteration of putting together the demo data, I did create a kind of a utility container for Nominitim that interfaces with the kind of out-of-the-box Nominitim self-hosted API. So if any of you are interested in non-US addresses, I think we'll probably be adding that, or at least adding functionality to support that alongside DGauss, because there are use cases where it is very valuable, of course, to have international addresses geocoded. But out of the box, or at least in this set of 6, DGauss is readily available. And this is, I believe, a small tweak on the kind of official DGauss image, or it might even be the official one. I'm not sure if where that's currently at. But in any case, you have a geocoder available in a container. And then the last 2, I've actually personally worked the most on. So Gaia DB is a Docker container that has Postgres installed together with PostGIS that you've already heard now mentioned many times. And in addition to just having those packages available, it is initialized with 3 kind of key schemas, or at least 3. There's actually more, but the ones that are shown here are the backbone, which is, it has a set of tables that represent the geometric and the attributes variables for a given data source. And it's this schema that you can actually populate with the set of functions that Robert mentioned in Gaia Core. So you can take a variable of interest, say PM2.5, and populate the tables in this backbone schema. On the fly, if you will. So this GaiaDB has a schema and all of the functionality to actually handle that. It also has the GIS vocabularies preloaded, and it's only going to have the delta tables. We cannot distribute, of course, the rest of the vocabulary just freely. That requires you to check an accept box on Athena to download. So, but we can distribute the GIS delta vocab that we have created ourselves, and so we build those actually into this image that you can run as a container. So those are here, and then the last bit is a kind of an OMOP schema that it comes out of the box empty, but you can then load in your location history table, and that is kind of where that kicks off the process to assigning and creating the external exposure. And then the final piece, as you'll notice, the nice little cover up with the external exposure, is the Gaia core. And this is where Robert and Kyle and others have really put in a tremendous amount of work to make these functions robust and flexible to accommodate different databases and different variable configurations and all of this. This is really what sits, as it's named, at the core of like the functionality to take these GIS data and get them into a format that you can actually start to do analyses with OMOP. And so we've built the Gaia core image on top of the Broadsea Hades image, for those of you who are interested or are familiar with that, which comes packaged together with RStudio. So the cool thing with this Docker image is if you spin it up as a container, you have a little instance of RStudio that you can access through your web browser that has Gaia core pre-installed with all dependencies. And then in theory, if you use also the whole orchestration around this, you have the Gaia DB and all these other tools fully integrated. So it's kind of a one-stop shop for your R plus everything else. So it's very convenient, especially if you have gone through the trouble of having to configure an R instance with all of the dependencies and do that whole thing multiple times. So that's then available, and it's again loading dataset variables into the backbone and then taking what's in the backbone, executing spatial joins to link a location history table into an external exposure representation. Okay, so I already mentioned this. So yeah, the kind of the base image for that Gaia core really is the Broadsea Hades. You can find it. It's on Docker Hub, and then when you run that, you actually get this RStudio web application that you can log into. So take a look at that if you're interested. Okay, and so this is the workflow that I talked about. And again, left side, location history, right side, external exposure. And this toolchain, or this set of containers, is facilitating like this left to right process, this kind of transformation from one set of tables into another set of tables. And this diagram does not do justice all of the stuff that's happening in that center column, because there is a lot. But if you don't take anything else away, just think I start with my location history, and I end up with this external exposure that has some sort of temporal representation of value for a person and a place. And so I'm going to quickly just zoom into each of these. I've kind of already talked about them, but we have DeGauss up here, and that in theory you would apply against your location table. So this is happening in GaiaDB, but you apply this geocoding on your location table to get the lat long values, and then even more, you end up with like a geometric representation of that. But this is going to then convert addresses or free text addresses or however it is into latitude and longitude. And of course, there's other geocoders that have been mentioned. Then you have the catalog itself, which Tim gave an awesome view on, and that catalog has its subcomponents. So catalog is a web app that's supported for searching by Solar, and then it also has the knowledge graph functionality to visually interrogate your data. Note also that this catalog, and at least Tim's catalog entry for the PM 2.5 data, does integrate the GIS vocabulary terms, which are actually hosted elsewhere on GitHub, but are built into GaiaDB natively. So that's the kind of catalog piece of this. And then the DB itself is where you're actually executing or able to execute the spatial join. So this idea of instead of joining like on exact matches of a column like you would in a traditional database, you're saying, all right, I have this geometry or this, let's say, latitude and longitude point, and I want to know if it falls within a polygon of interest. And so PostGIS has the underlying functionality to kind of make those assignments and to do so in a vectorized way that's efficient and quick. And then you end up with Gaia Core, and Gaia Core is what's effectively orchestrating and kind of running this show. So it has the functions to take your data from the left to the right of this, and it uses these other tools, or it works together with these other tools to get you there. And so once you've done that, then you have an external exposure and your vocabulary tables. And our idea at the moment is the output from this process, so specifically the external exposure and the delta vocab, would then be uptaken back into your OMOP instance, and you could then just run, like, essentially as a CSV load to a data table, and then you can proceed with the rest of your processes. So this is kind of its own little isolated environment of containers. You start with those two tables, your location history. You run through this awesome process where you're selecting your variables and your geocoding and your spatially joining. You end up with your external exposure, and then that is what you're taking with you back to the kind of the central OMOP instance to start to do some of these GIS specific analytics. So that's more or less the ETL pipeline. And I actually went through that quicker than I expected. I think that was my last slide. Yeah. So I do have time for questions. If you have any on that, I know I went relatively quickly through some of those more complex concepts, but happy to field anything that anybody wants to ask.
Jared, that was great. This is Tim. I was just going to say, I don't know if you could share the Tufts Broadsea GIS land URL with everybody. I shared it on the chat, but everyone in the room hasn't had a chance to see it.
Oh, awesome. Yeah, I will. I'll pull it up just a second. Thank you for sharing that. Let's just share my screen again. All right. Can you all see this?
Yep.
Awesome. So this is a fork. So for those of you who are familiar, Broadsea is kind of a containerized version of the OHDSI tool stack. And there's lots you can create different profiles within Broadsea. You can do different things with it. You can use it to spin up an Atlas instance or have Hades packages available or all of these other things that you would do. And we have created a fork of Broadsea specific to GIS with the intention that we will eventually merge this and integrate it back into the kind of central Broadsea toolkit. And this is actually all of this work, or most, if not all of it, has been done by Tim. So awesome work on that. But in this, you can find and I think it's Tim. You're working off of the containerized? No, you're working off here. I think. Let me just quickly see if I can find the GIS subset here.
It's the main branch, and if you just look at the README, I actually included instructions in the README under a section called Gaia,
GIS.
I think.
Gaia.
Yeah. It's at the very end.
All right. All right. So the last, I guess, the previous set of slides were really to go through if you have location data and you have variables of interest, how you take that into kind of this joined instance or joined table with values associated with people and times and places. And what I'm going to talk about in these last slides are really once you have an external exposure together with your location and the rest of your EHR data, how do you actually build a model using the OHDSI tools that references those data and can do so in a meaningful way? And so I already kind of introduced the use case, right, of building a patient level prediction model, so PLP, that looks at trying to estimate the risk of developing or being diagnosed with COPD based on both your EHR data and your environmental residence exposure to PM2.5. And in terms of motivating at least the analytical integration, these GIS extension tables specifically haven't yet been integrated into kind of the broader OHDSI tool stack, if you will. So you can't go into Atlas and create a cohort based on an external criteria. That's not yet possible. But you can still reference external exposure and actually really any data set in a OMOP-based analytic workflow through the PLP package. And so I went on this journey, as we do, I guess, in OHDSI, to figure out how actually practically to do this. And I was able to get to a model that pulls in the PM2.5 data. And I will show a little bit about what that looks like. And if you go off and want to use this on your own, how you might be able to do something similar. And before I dive into that, I do want to give a quick terminology note. So there's a couple of terms that I will probably use interchangeably. The PLP package specifically in its data model references covariates. So a set of kind of attributes about your data set that is calculated in some way. Those are often termed features in other contexts, and the functions specifically in the PLP package are referred, like they refer to them as features. So this covariate feature thing, I might be interchanging them at a high level. This will make more sense as I go through, but I just wanted to kind of give a quick shout out that covariates, when I'm talking about them, you can think of them also as features in this case. All right, so this is a slide that Andrew showed already for patient level prediction. I'm not going to go into the intricacies of patient level prediction. Jenna Reps, if you see her walking around the conference, is like the guru or one of the gurus in this. Definitely flag her down and she'll talk to you about it. But at a high level, we have an observation window where we're able to see the patient's EHR data, and we have then a period where they are at risk for some outcome of interest, in our case, COPD, and we want to be able to predict the likelihood that they're going to kind of be diagnosed or have that outcome within that time window. And traditionally, at least within OHDSI, this is done with your EHR data, specifically in the OMOP data structure of the data model. And we would like to then add GIS data, and in this case, in the specific use case, PM2.5 data, into that kind of observable window, and then use it alongside these other covariates or features in order to train and make these predictions. Okay, so the first step in all of this is the cohort creation. And I already talked a little bit about the stratification of the synthetic data into COPD and non-COPD patients, for those of you who were there, I guess almost 3 hours ago. Briefly here, I took the tough synthetic data, so this EHR representative data set, selected those patients who have COPD or that were diagnosed at some point, and placed all of those in my outcome cohort. And I did this in 2 ways, once with Atlas, once with SQL. And I created this outcome cohort, and I looked at that outcome cohort, and I evaluated the distributions of gender and age. And from the remaining non-COPD patients, I selected a second cohort of representative patients in terms of age and gender to my outcome cohort, and combined those all together in what I'm calling the target cohort. So my target cohort then has COPD and not COPD patients. That's kind of this group of people I'm interested in, and that really is what's making up this GIS synthetic data, as if you will, like this subset of the Tufts data together with GIS. And then the outcome is really the COPD patients. So those are, when I refer to the cohorts, those are what I'm talking about here, and that becomes more and more important as we go through the PLP building process. All right, so the actual cohort creation, the logistics of this. I have I already talked a little bit about this, simplifying it, so there's not a lot of logic happening here. The view on the left is Atlas, which is more or less saying that I want somebody to enter my cohort if they have been diagnosed or have any sort of condition occurrence entity related to COPD, the concept, or any of its descendants. So that's very, very simplistic view of a cohort, but that captures at least these patients, and you'll see the specific concept that I used you can find in Athena. It's this 255573 for those interested. So that's how we did it. I have a SQL query. Again, I think I posted a link in a previous chat or in the previous talk to where you can find a full write-up on the synthetic data. That's where I actually did this, but we created the cohort. Then what you can do is to create a generic patient level prediction model, and I'm using a logistic regression model. You can go wild with the number of settings and training settings and covariate settings, all of this stuff. There's a lot of different knobs you can turn depending on your use case. Keeping it simple here, I pretty much defaulted the model, or I kept with the default configuration. So it's a logistic regression model, and I had my target cohort, which is again all the GIS patients, and my outcome cohort, which is GIS COPD. And then I exported this model. And again, for those of you who aren't familiar with Atlas, you can export then a PLP model as an R package that you can then load in an instance of R and actually train and evaluate and share and then validate elsewhere and do lots of cool stuff. So this is very powerful. I did this first with Atlas. You can actually also do this programmatically. If you say, I don't want to deploy Atlas, I just want to like dive into the PLP package, you can create a PLP model with just the PLP package, and there's a set of functions. This is one of them that you can use to do it, which is actually running multiple PLP. But in any case, you end up with this package that can be trained. And a key output from that package is your PLP data object. And so what that data object is more or less, it contains information about your two cohorts, in this case, my outcome and my target cohort, together with two entities that are relevant. So covariates, which again features covariates that contain attributes about the underlying data. So it's a kind of abstraction of the data, together with labels. And labels in this case are fairly, like if you look into how the sausage is made for PLP, labels is like a broad matrix that has a lot of information in it, from like date of birth to gender to, there's a lot of elements that are considered labels in this data set. And that's going to be important. So keep that in mind later on, for later on, I should say. Okay, but you create your PLP data object using a generic model. Again, nothing with external exposure. Everything is like vanilla OMOP, just getting this PLP data object as you want. All you need are your two cohorts of interest. And then what you can do is you can split that PLP data object into a testing and a training set. Typically, there's like a 75-25 split, but you can also change how you do that, and also the way that it's split and the sampling, and there's a lot of kind of statistical relevance to how you do this. Or you can just, again, choose a default split. And there's a function in PLP, in the PLP package called split data, that will do this for you. So you split your data, and now you have this nice test and train set. And for those of you who are more familiar with modeling, this should look very familiar. Okay, and this is where we start to bring in the GIS data. So we have our split data set, and we have our external exposure table. And here what I've done is actually kind of created a further abstraction of the external exposure table. If you remember back to the synthetic data, I created one external exposure row per patient, per year of living in that location. So like a given patient could have 18 exposures, with each referring to each annual value of the place that they lived. And in this case, I just extracted their mean exposure over that time period in the city that they're assigned to. So you end up with this PM value that's associated with a person. And I placed then that PM value for the PM 2.5 concentration, the annual average, as an additional label in this labels matrix that has one row per person. So then they receive essentially a pollution value that is their label. And again, all of the code for this you can actually run on your own. You can try it out and do it. Like, it's all available in the write-up. Again, I will also post that in the chat afterwards, and I have reference to it on the slides. But at this step, we are just augmenting the labels, and those labels are then used in training to do some fitting, and I'll show you why that becomes more important in just a second. But right now, after this step, we have our base covariates, so we don't have any covariates that are specific to external exposure. We only have a label estimated outcome that is relevant for GIS. And so what we have to do is at this point, we follow the vignette. And if any of you have experience with the PLP package. Specifically, there are a lot of vignettes, one of which is how to add your own custom features. And it's a thorough vignette, but it doesn't give a lot of context for where you should start and where you should end. So I thought that I would try to provide that context here in terms of like, you have to split your data, you have to update the labels, and then you can get to this point where you can start to add your custom feature functions or custom covariate functions, or however you want to call this. And so what you do is you create two functions, and I'm not going to, again, Vignette talks a lot about this, but you create two functions, and the implement function is critical, and that's actually where you are fitting a model to the labels. So what you're saying is, I know my my outcome of interest, in this case, does the person have COPD or not? And I know they're labeled average PM value for that person. And so I fit a model based on like those two factors. So my X in this case is the value of the PM, and my Y is outcome of interest, 1 or 0. Do they have it or not? I run it through a GAM fit. So GAM is a statistical package in this case from R. And that produces then for me in this case, it was a cubic spline, I think, fit of those data that then I can use as my fitted values for my trained covariates, or to update my covariates in a trained data set. And that model then I can pass on and actually run against my test data set. And I'll show you that in just a second. So we now have, and I kind of slightly skipped over a step here, but you run your your trained data set through this implement pollutants model. It spits back an updated set of covariates together with a model that it used to actually produce them. And then you use that model to estimate the updated covariates in your test data set. So you're kind of augmenting that, and you end up with your split data that has not only now new relevant labels, but also new covariates that are directly referencing a GIS variable of interest. In this case, it's just one, but you can imagine expanding that label space to not just a scalar value, but like if you wanted to, like a whole JSON with lots of different attributes, and you could go like really the sky is the limit here. This is a very simple use case, but at this point now you have your test data and your training data that has kind of your necessary abstractions of the GIS information to actually train and run and evaluate the PLP process. A little bit of note here. So when I actually fit my covariates, this is the fit that came out. So when you talk about doing that kind of cubic spline fit between the concentration PM 2.5 and the outcome of interest, this is the relationship I got, which if you think back, that is very nicely aligned with the forcing function that I used to assign people to places in the beginning. So this covariate fit, while like 0 means the person doesn't have COPD and 1 all the way up here means that they do, I ended up with the relationship that I used to effectively distribute people to the locations at the very beginning of this, which is an indication that this was at least like the underlying model is coming out in my covariate training process, and that's a good sign. That means it's kind of seeing this underlying forcing function. So that was already encouraging. And at this point, then you have your fitting and testing process. So then you take this training data, you fit it. So you actually kind of create your weights in your model. In this case, it's a logistic regression. You can think of it like y equals mx plus b. You're finding m, in this case, the slope that fits your data points. And with those weights, you're then evaluating them on your test data set, which again also has these covariates of interest that you want to evaluate for GIS. And it's the output from this test data that's really kind of giving you an indication of whether your model was trained appropriately, or that's kind of your mechanism for evaluation. And what the PLP model or PLP package also has is, once you've done this and you've trained a model and you've done it and kind of tweaked all these different knobs to suit your use case, you can package this up and you can send it off to somebody else with the same data set, and they can run it and validate it and see if they're seeing a similar kind of response, if they get also if the model is able to predict like a similar outcome when it should be expected in their data. Okay, so now we've been able to take, I guess at this point, we've been able to take GIS data, create or update our labels, update our covariates, then train and kind of fit the model. So we capture our weights, we test that fitted model on the test data. And this is kind of the start of the iterative process. Like I said, like this is then when you would say, okay, maybe the logistic regression isn't working so well. Maybe I want to use a neural net, or maybe I want to switch over to some other clustering method that could do this. In any case, this is kind of the end of your model, or your one iteration of model development in this case. And I'm getting close to the end of time, so I'm not going to go too much into the results, but one of the outputs that you can take a look at when you develop one of these models is kind of a covariate importance table, which in itself doesn't give necessarily a ton of information, especially with regard to things like causality. But what it does do is it shows you the level of importance assigned to a given covariate or feature by the model. So remember, we have these covariates, again, abstractions kind of our underlying data. And the fitting of the model is producing weights that are assigned to those covariates. And the size of those weights is, in this case, kind of, it corresponds with the importance of that covariate in your model. And so what I'm showing on this slide is the top 10 most heavily weighted covariates in this model. And the PM2.5 exposure, while not the most importance, is up there. It did influence the outcome of the model, and it did improve the prediction accuracy over a model like the generic model that I trained without it on the same data set. So all that to say, you can take one of the, and again, this is the custom, I just did the covariate ID, it's the same as the concept ID. So this is the custom concept that Paulina and others put together and defined, going all the way through the process of the tool chain into an external exposure, and then getting kind of integrated into this PLP workflow to where it can actually be used in a model training scenario and influence the accuracy of a model. And again, this is not EHR data. This is actually publicly available data that was captured via satellite in this case. And you can imagine, I mean, it's exciting for me to see this just because it's, even in a simple case, you can already see that this will influence outcomes fairly considerably. And you can imagine as you start to integrate SDOH and other GIS variables and things like that, there is a conceivable and actually feasible workflow for doing so. And so kind of on that note, next steps for this process. So I think expanding the workflow, I kind of already mentioned, to generalize to multiple exposure occurrences, external exposure parameters. So like I said, I just used a scalar value in that label column, but you can, there is no requirement on data type in that matrix. And you can imagine having like a very dense data object in that column that either represents temporal relationships or additional variables of interest and whatever you want, and running through the same process. And then I also mentioned this, but this case was it was simplified in that it wasn't temporally related. It was the average value of exposure for a person over a given time. And it didn't take into account like how long they were exposed before something else happened, which would be arguably a much more interesting phenomenon to study, but was beyond the scope of this demo. And then the second piece is really trying to evaluate the same workflow, but against a real data set with like true data and true locations assigned to patients. So I think that's the next big step, and that's something that we're preparing for, at least at Tufts, and I think at other institutions, especially now with this containerized set of tools, becomes much more readily available and accessible. And then hopefully this time next year, we will be presenting on some of that preliminary real work. So yeah, I guess that's the last slide of my talk, but thank you very much for listening. And I hope that you all are excited about this as I am, because it's very cool to see it all come together like this. So.